Hi there, welcome to a new video series on complex analysis. We're going to consider a variety of different topics related to complex analysis. We're going to show what complex functions are. We're going to show how to map between different complex planes. We're going to show how we transform these different variables, the different types of transformations that you get. We're going to show how to differentiate complex functions and a variety of theorems associated with it. We're going to show how to integrate. We're going to show how to transform, and lastly, we're going to consider different series expansions of complex functions, the Taylor series, Maclaurin series, and also the Laurent series. We're going to show if these different series converge, and the final thing is what are residues and the residue theorems. So before all that, what is the purpose of studying all of this? What is the value of knowing complex analysis? So when we say complex analysis, we're talking about functions with complex variables. And we know complex contain imaginary numbers. The word complex is associated with the square root of -1. So we're talking about functions that have these complex variables in them. What is the value of studying all of this information? Well, we can solve a huge range of problems in physics engineering knowing complex analysis. An example of this could be in fluid mechanics. Fluid mechanics is something that many different types of engineers need to know about, be it chemical engineers, mechanical engineers, civil engineers, and so on. So in fluid mechanics, we're often considering the airflow around different shapes, right? So airflow. And we can have many complex shapes, difficult shapes. We can have, for example, the wing of an aeroplane. We could have process equipment in which they are shaped very oddly. So how does complex analysis help us here? Well, we can take those complex shapes and simplify it into much simpler shapes like a circle. So in here, we can take difficult shapes and we can actually convert them into simple shapes like a circle. So we saw in the different topics, the word transformation was used, mapping may have been used as well. So this talks to all of that. So let's move on into the introduction to this particular field of study and how we go about using it. So we know from our studies of calculus and basic mathematics what complex variables are. People use the symbol I or J, and usually it means the square root of -1. So in the study of complex numbers, we would usually represent a complex number by z, and we would say z is equal to x plus jy. If we are representing complex numbers into the plane, we would call it the z-plane, and there would be a real part associated with x and a complex part which would be y. So we would just plot it. We would have x and y, and we would plot a point. And that point would be the real component, that's x, and the imaginary component, y. So we say that we are plotting it in the z-plane. A simple example of this could be z is equal to 2 plus j. So the real part is the x value 2, and the imaginary part is 1. That's what y is equal to. So now we have a complex variable, that's z, made up of complex numbers, j, and these variables x and y. So where complex analysis comes in is when we start considering functions of z. So in the same way that we can have y is a function of x, we can now have functions of z. And instead of calling it y, what many people do is that they call it w. So we say w is now a function of z. And it could be, for example, z plus 2 or z squared or something like that. So there is a relationship between z and there's some input z and there's some output, some function of z. And z is made up of complex numbers. So in the same way that we split z into a real part and an imaginary part, we can now take this function that we have created, w, and split it into functions of z. So we said that w is equal to fz, so we'll just use z squared as an example. So we'll say w is equal to z squared. So we can substitute in the variable z. So z we know is x plus jy, and now we're squaring it. So if we do that, we get x squared, then we have plus 2jxy, and then minus y squared. Remember that the square root of j is minus 1, so we have the square root of minus 1 squared, and that will give us minus 1. That's why we have minus y squared here. J squared is minus 1. So now we can group this together. We'll say x squared, then minus y squared, plus 2jxy. So we can now split this into a real part and an imaginary part. So this x squared minus y squared, that will be our real part. So we can call that u. We'll say that u is some function of x and y. Now this imaginary part, that's 2xy. So 2xy, that's our imaginary. And we'll call that v. Say that v is a function of x and y. So this is our transformation equation. That's what we mean by a transformation function or transformation equation. This is how we go about transforming this variable z into a function of z. And the example used was z squared. So we can write w, the function of z, as being u plus jv. So how would we actually do a transformation? It's simple and straightforward. We would just apply this transformation equation. So if we have some variable z, which is equal to something like, maybe the example earlier we used was 2 plus j. So we have our z-plane associated with this. So there's our z-plane. And we have our point. We have x is equal to 2. There's x and y is equal to 1. We'll call that point P. Okay. So what is our transformation? Our transformation now is into a function of z, and that function is w. So we're no longer talking about the z-plane, we're talking about the w-plane. So that's the w-plane. So in the same way, z was imaginary with y and real with x, with xy, and now w is with u and v. So we have u and v on these axes. So this point z, 2 plus j, has a corresponding point in the w plane, and the relationship between them is u and v. So you remember that u was equal to x squared minus y squared that we had shown on the top here. So x is equal to 2 and y is equal to 1. So we have 2 squared, which is 4, minus 1, which is equal to 3. And we remember that v was equal to 2xy. So this is equal to 2 times x, which is 2, times 1, which is just 4. So this w is equal to u plus jv. So what w is equal to is 3, that's the real part, plus jv, and v is equal to 4. So we have 3 plus j4. So to plot it in the w plane, we would simply identify 3 and 4. So it might be here, for example. So this p is p prime in the w plane. So we have transformed p into p prime. So that transformation between these two planes, the z plane to the w plane, is what they call a mapping. So we would say the terminology is we have mapped P onto P prime. So P prime is also called the image of P. So just to summarize once more everything that we have just done, we are now talking about functions with complex variables. We would associate a complex variable z to have a real part and an imaginary part, and we now transform this z variable into a function of z. So we call that w. W is a function of z, and we use the example of z squared. And then we used the definition of z, and we created an expression for the function of z in terms of x and y. We then lumped these expressions into a real part and an imaginary part. So we said this transformation equation w now consists of a real part u and an imaginary part v. And we simply showed that we can take a simple example, complex value of z, and how we project that into the new plane. And going from the z plane to the w plane is a mapping. In this video, we're going to talk about linear as well as non-linear transformations. This is of lines and curves between the complex planes. So on the left-hand side here, we have 2 points. We have point A. So A is 1 plus 2j. So if we were to plot it, there's A here, there's 1, that's the real part, and 2, that's the imaginary part. And then also we have B. B is 4 plus j. So we have 4 on the x-axis and 1 on the y-axis. This is 2 z coordinates. So the question is, these two are joined by a line. Okay, so we now need to basically convert this line into the w plane. Okay, and the transformation equation is w is equal to 2 minus j3 times z minus 4 plus j5. So this is how z transforms. Okay, this is how z transforms into the w plane. So if we were to convert this a and b into its corresponding coordinates a prime and b prime in the w plane, we would just apply this equation, this transformation equation. So doing it with a prime, so all we do is we substitute, instead of z, we substitute the coordinates of z. So we have w is equal to 2 minus j3, that stays the same. And instead of z, we have 1 plus 2j, so we put that in, or 1 plus j2, the same thing. Then we have minus 4 plus j5. And we just simplify this. We have 2, that's 2 times 1. Then we have plus j. So we have 2 times 2, that's 4j. Then minus 3j gives us j. And then lastly, we have 3 times 2, which is 6. And then we have j times j, which is minus 1. So we have minus 1 times this minus gives us a plus. And then 3 times 2 is 6. So we simply have plus 6. And then we have minus 4 plus j5. And that gives us 4. That's 2 plus 6 is 8. 8 minus 4 is 4. So we have 4 plus 6j. So this is the point, a prime, right? So that's what a prime is. It's 4, that's the real part. And then 6 is the imaginary part. And then we can do the same with b. So that's a simple matter to do that. We would say w is equal to, again, 2 minus j3. Then we have 4 plus j is z. And then minus 4 plus j5. And expanding this out, what we get is 2 times 4 is 8. Then we have 2 times j. And then we have 3 times 4 is 12. So 2 minus 12 is minus 10, sorry. So minus j10. And then lastly, we have minus j times j, that gives us positive 1. And then we have 3 times 1, which is 3. And then minus 4 plus j5. And then simplifying this, what we get is 7. So we have 8 minus 4, 8 plus 3 minus 4, that's 11 minus 4, which is 7. And j10 minus, so minus 10 plus 5 is minus 5. So this point b prime corresponds to 7 and minus 5. So we can do one of several things at this point. We can see that, a straight line in the z plane basically corresponds to a straight line in the w plane. So we can get this equation of this line here, y is equal to mx plus c, and that's in terms of x and y. The w plane is made up of u and v, so we can also get an equation of this straight line here. We could do it in the traditional way, find the gradient and the intercepts and all of these things. Alternatively, we can substitute z in terms of general coordinates into this transformation equation, and then we can get an equation for this line in terms of u and v. That's doing it analytically. However, it's important to make a point when we're converting between different kinds of lines between the z and w plane, that there is a transformation, okay? There is a transformation that basically makes one line into the other line in the other plane. If we look at a general form of our transformation, we have w, okay? So w is a function of z. And if w is equal to z, then what happens is they look exactly the same. So what is in the z plane will appear in the w plane. Now, if we were to multiply this by a number, right? Let's just say that number is a. Then what we have done is we have scaled this value of z. We have scaled this value of z. So this line, which we have just done now, it becomes larger in size. In other words, it's magnification. So the word that's used is magnification. So to calculate the extent of the magnification, what we need to do is we need to take basically the size of A, okay? So the size of A would essentially tell us how much bigger is this particular line in terms of Z, how big is it scaled up? So the size of A. So the size of A, we just use the theorem of Pythagoras, and we can see that in this transformation equation, there's Z here, and we have A in front of Z, okay? We have A in front of Z. So this 2 minus 3j is actually what A is equal to. So A is equal to what's in front of Z, that's 2 minus 3j. So if we find the size of this using the theorem of Pythagoras, the square root of x squared plus y squared, so 2 squared is 4, and minus 3 squared is 9. So 9 plus 4 is 13. So essentially we have the square root of 13. Okay, square root of 13 is roughly 3.6. So what we're saying is that this line is roughly 3.6 times bigger, okay, in size. So this line that's here, it's now made 3.6 times bigger, okay? So what this A also tells us is rotation. So this line is bigger. We can see that the final line here, okay, this is what we get, that it's bigger, okay? It's 3 times bigger than this original line. So it's also rotated. So it's no longer this angle here, it's this angle here, okay? So how we calculate that rotation is also by looking at the value of A. So in terms of how much it's now rotated, we look at the argument of A. So this is actually just arctan. Okay, it's arctan y over x. This is the y and x values associated with A. So what this is arctan, essentially y over x minus 3 over 2. And that is equal to about 56.3 degrees. Or rather, minus 56.3 degrees. So what we're saying is we have now roughly tripled the length of this line, and we have to rotate it clockwise a certain length, okay, a certain in terms of the angle. So the last thing that happens is what's called translation. So in terms of translation, what happens is that there's a shifting. So we have W is equal to AZ, and then all we do is we add B to it. So this B tells us the extent of the translation. There's our original transformation equation here. This is A, that's Z, and then this part, okay, this part is actually B. So it's plus B. W is equal to AZ plus B. So this is what B is equal to. So what is the translation? We have minus 4, that's the real part, and plus 5, okay? So what this means is that the final line is shifted 4 units to the left and 5 units up. That's all that there is to it. So the moral of the story is that we can apply this magnification, rotation, and this translation to this line just by looking at this equation, and we will get this final product that's in the UV plane. So that is an example of a linear transformation. So we can also look at a non-linear transformation. So there is an illustration of that. So we have a straight line in the z-plane, and the coordinates of this straight line, the two endpoints is A, and A is given as 0 plus J4, and B is given as 4 plus J0, okay? So we now want to understand what this looks like in the W-plane. So if we have a straight line in the Z-plane, and we have a transformation of the form W is equal to AZ plus B, then we will, of course, have a straight line in the W plane. So if we have W that's now a non-linear function of Z, then we'll have something different. So the example that we're going to consider here is if W is equal to Z squared. So that's W is equal to Z squared. So what we're going to determine is what does this shape look like in the W plane. So the first thing that we're going to do is substitute generically what Z is. So Z is x plus jy, that's the generic form, and we're squaring this. So what we're going to get is x squared plus j 2xy, and j is square root of minus 1, so minus 1, so square root of minus 1 squared is going to give us a minus here, and we're going to have y squared. So if we gather these terms, we get x squared minus y squared plus j 2xy. And as we had done in the last video, we're putting everything in the form W is equal to U plus Vj or Jv. So we can see, if we compare this, that U is equal to x squared minus y squared. So U is equal to x squared minus y squared, and V, okay, is equal to 2xy. So what we're going to now do is express each of these things in terms of u and v, okay? So we're going to get basically values for u and v. So if we do that, let's look at this line. The equation of this line is y is equal to 4 minus x. Okay, this is a straight line equation, y is equal to 4 minus x. We can substitute that in. So we'll do it here. So u is equal to x squared minus 4 minus x squared. And if we expand this out, what we're going to get is x squared minus 16 plus 8x minus x squared. And if we simplify that, this x squared and x squared will cancel off. We're left with 8x minus 16. That's what u is equal to. So now we have an expression for v as well. So if we do that, we have v is equal to 2x, and we would remember that y is 4 minus x. So that means that v is equal to 2 times 4 is 8. We have 8x minus 2x squared. So what we can now do is we can get a value of x here. We can just say that x is equal to, okay, we take that to the other side. We have u plus 16, and we divide it by 8, so we have 1 over 8 here. So if we have an expression for that, so what we can do is we can substitute this value for x in terms of u there, okay? So this means that v is equal to 8 into x, and we saw that x is 1 over 8, all of the stuff. So we have 1 over 8 into u plus 16. And we have minus 2 into 1 over 8 u plus 16 squared. We can expand all of this stuff out. So when we do that, we get 8 times 8, that is just 1. So this whole thing just becomes u plus 16. And now we expand this rest of this stuff out. So 1 over 8 squared is 1 over 64. So 2 divided by 64 is 1 over 32. So we have minus 1 over 32 u squared. Okay, so expanding this inner part out, remember we have minus 1 over 32 on the outside, and then we have 2 times u times 16, that's 2 over 32. So this 32 will cancel out with the 32 that's already in front. So all we're left with is minus u. And then finally we have 32 in the denominator. We have 16 squared, and 16 squared is 256. So 256 over 32, that gives us minus 8. So that's what all of that simplifies to. And I think we're pretty much done. So that u and that u will cancel out. So what we're left with is minus 1 over 32 times u squared minus 8. So this is what v is. So we have a relationship between v and u, and we can see that it's a parabola. So that is the relationship between u and v. So in the w plane, what we're actually going to see is a parabola. So if we were to find the endpoints, we can do it with the points as we have done it traditionally. So what is a prime and b prime? So for a prime, all we need is z squared, okay? So that's the relationship between the two. So x plus jy squared. So x is 0, okay? And then y in this case is 4. So we have 16, okay? We have 16j. Or rather, j squared is going to give us minus 1, right? Sorry, square root of minus 1 squared is minus 1. So all we're going to have at this point for a prime is minus 16. This becomes minus 4 squared, which is equal to 16. Okay, and with b, it's the same thing. We have 4 here and then 0. So we just have 4 plus 0 squared, which is 16. So our two coordinates is basically minus 16 and 16, right? We can say plus 0j. So there's no imaginary parts here. So that's what we've plotted. We've plotted minus 16 and 16. And what is the relationship between u and v? We derived the relationship just now. We saw that v is equal to minus 1 over 32 u squared minus 8, sorry, plus 8. Sorry, this should have been a plus 8 here. So 16 minus 8 gives us plus 8. So what we're saying is that the relationship in this W plane is a parabola, and that's the equation. So it's going to look something like this. Okay, that's not a great drawing, but you get the idea. So it goes something like that. So here's A prime, and then here's B prime, and then joining it is essentially that parabola, that curve. So this would be an example of a nonlinear transformation, how we go about transforming a different set of points, maybe a straight line. We have different transformation equations. One is linear and the other one is nonlinear. And for linear, we can say that, you know, it's a combination of magnification, rotation, as well as translation that results in how it looks finally in the W plane. And with a nonlinear transformation, we can actually analytically find the relationship between u and v, and we can show, okay, this is what it's going to look like. In this video, we're going to talk about differentiation of complex functions, and we're also going to look at differentiation in the complex plane. This culminates in what's called the Cauchy-Riemann equations and how they're used to establish if a complex function can actually be differentiated. So traditionally, we would have some function of x and the derivative f prime x, also called dy dx, is merely defined as the limit. Okay, we have the limit of some incremental change. We'll call it delta x. That approaches 0. It's often called h in many different textbooks. And you know what's being taken the limit of is usually some function, the incremental change in the function, subtracted by the function itself, and divided by the increment. So this is standard elementary calculus. Okay. So how does this apply to the complex plane? So let's try and establish what we're talking about when we want to understand the derivative of a complex function. We know that we have two planes, right? We have the z plane. This is the z plane, and it has a complex variable, and maybe there's some line. Okay, there's a line that's defined, and of course each point along this line will have a corresponding x and a corresponding y, real and imaginary parts. And then this function is transformed in some way into the w plane. And the link between the z plane and the w plane is the transformation equation. So if we have something with respect to z, okay, so this is z, okay, a collection of points of z. So when we speak about delta z, so delta z is some differential change in this function that's in the z plane. So this function z, okay, this collection of points, would have had some equivalent collection of points, w, associated with each one of them. So the moral of the story is that this differential change delta z has associated with it some differential change delta w in the w plane. Okay. So when we speak about derivatives in the complex plane, what we're asking is, when we have some differential change z, complex variable z, how much does w change by? So what is the rate of change of w as z is changing? So this is essentially what we want to establish in terms of the derivative. And we would consider the limit as delta z approaches 0. So we also know that w is equal to some function of z. Okay. So we actually want to determine dw dz. That is the derivative. How much does w change when z changes? So how is it defined? Well, it's defined in exactly the same way as the traditional derivative is defined. So we would have something like f prime z, okay, and that would also be equal to dw dz. So everything that is written here also has an analogy in the complex plane. So dw dz is equal to the limit as delta z approaches 0, and instead of x plus delta x, what we would have is f into z plus delta z minus f of z divided by delta z. So this is the derivative of a complex function. Okay. So the same differential rules apply. So if we have f of z is equal to z squared minus 4. So what is f prime z? Okay, what is f prime z? So f prime z is simply 2z. So this is all easy and straightforward. So the question and where the complications arise is, does f prime z actually exist? So that's the question. That is what we actually need to establish. Okay. So if f prime z exists, that's all well and good. Okay. Then the other question is, does f prime z have a unique variable? In other words, is there only one derivative f prime z? So there's two things that we actually need to ask ourselves. The first one is, does f prime z exist? And the second question is f prime z unique? So does this actually is asking, is there only one derivative? In this case here, we have 2z, right? So that's just one derivative. So we need to establish all these things. So what the Cauchy-Riemann equations do is actually help us, okay? So f prime z exists. So in general, we have fz, and fz is actually called an analytic function. So this terminology is used quite a bit. It's an analytic function, and sometimes the word regular is also used. It's a regular function. So in general, the derivative will probably exist if it's an analytical function. So what is an analytical function? Analytical function means that at a certain point z, we can choose some random variable here. So we have a point. And at that point, we have a defined value of z. Okay, that's number one. And number two, it has a single value. Okay, that's x and that's y. So we have a single value. That means we have one single real and imaginary part. So if that happens, then it means we have an analytical function. So an analytical function is likely to have a derivative. So that's the first one. Okay. So we need to say a function is analytical. So the second one is f prime z unique. So that's where the Cauchy-Riemann equations come into play, and it's quite straightforward to actually derive. So we have w in the w plane, and we said that's u plus jv. And we have delta w, some incremental change that would be associated with an incremental change in u and an incremental change in v. We have z as well, and that we have also described as being x plus jy. So an incremental change in z is an incremental change in x and an incremental change in y. So if we are saying f prime z, okay, then what we're actually asking for is dw dz, and we're asking for the limit as z approaches 0 of delta w divided by delta z. Okay? And what's delta w? Delta w is this delta u plus j delta v. So that's delta u plus j delta v, and then divided by delta z, and delta z is delta x plus j delta y. So now we have this thing here, right? Okay, I should also write the limit in front. So this is the limit as z approaches 0. We don't actually have z in this thing, okay? We don't actually have z. But we do have x and y, and we know that actually z is made up of x and y. Sorry, there should be a delta there as well. So what we can do is that we can break up this specification that delta z must approach 0, and we can split it up into two, okay? So we can split it up and say delta x should approach 0. Okay, that's not written very well. Let me just write it a bit better here. We can split it up and say that delta x can approach 0 and delta y can approach 0. So that's what we're going to do. We're going to do both, but we're going to do it one at a time. We're firstly going to let delta x approach 0, then we're going to let delta y approach 0 of this particular term that we have here. So if we let delta x approach 0, so let's write that down as the first step. So we let delta x approach 0. So when we do that, what we're left with is the limit as delta y approaches 0, okay, because we've already taken the limit of delta u plus j delta v divided by j delta y. Okay, and remember what we're actually calculating. This is f prime z. Let's just divide this. So the limit as delta y approaches 0. So we have delta u divided by delta y and delta v divided by delta y. So let's just do the second term first. So this j divided by j is just going to give us 1. And then what we have is delta v divided by delta y. Now we have 1 over j, right? We have delta u divided by j delta y. So 1 over j, what we're going to do is multiply this by j over j. Remember that j is the square root of minus 1. So we have 1 over the square root of minus 1 times the square root of minus 1 over the square root of minus 1. So the square roots essentially give us cancel out. So we have basically square root of minus 1. Essentially, we have minus j. So that's what's left. So we have minus j. So 1 over j becomes minus j. And we have delta u divided by delta y. You would remember from the previous videos that u is a function of x and y. So u is some function of x and y, and v is also a function of x and y. So this is actually multiple variables. And you would know now, if we're dealing with multiple variables, we have to deal with partial derivatives. So this delta v, delta y, as we take the limit as delta y approaches 0, becomes day v, day y. And this j becomes, well, it stays the same, and then delta u, delta y becomes day u, day y. So this is the first equation, important equation. That's a part of the Cauchy-Riemann equations, but we still need to get there first. So we let delta x approach 0. That's what we have done. So what we're going to do now is the reverse. What we're going to do is we're going to let y equal to 0. We're going to let delta y equal to approach 0. So if we do that, okay, there's our original equation. If this approaches 0, what we're left with is just delta x in the denominator. We can write that out. So we have the limit as delta x approaches 0 because we have taken delta y. And we have delta u plus j delta v divided by delta x. We can divide it as we had done before. So that's the limit as delta x approaches 0 of delta u divided by delta x. That's delta u divided by delta x. Then plus j delta v delta x. And in the same way, we get simply day u dx plus j day v dx. So we have f prime z and we have f prime z, but we have two equations, yeah, right? We have two equations for f prime z. So if f prime z has one derivative, in other words, has a unique derivative, remember that's what we're considering, is f prime z unique, okay? Does it have one derivative? So if there is only one derivative, it means that these two equations must be the same because they are both f prime z. So we have to make them the same, essentially. We're making it's the same as a condition. So we're going to say that day v, day y minus j day u, day y is equal to day u, day x plus j day v, day x. We will now equate the real parts and the imaginary parts. So if we equate the real parts, so what that means is that day v, day y is going to equal to day u, day x. Okay? And it's also going to mean that day v, day x is going to equal to minus, right? There's a minus sign there, day u, day y. So if we remember our example from earlier, we had f of z is equal to z squared minus 4. Then we can show via this condition, by the way, this is what's called the Cauchy-Riemann equations. Cauchy-Riemann equations. So these two collectively form the Cauchy-Riemann equations. So let's apply it to this example. Okay, let's get everything in terms of x and y and u and v and all this stuff. If we do that, we get f of z is equal to x plus jy squared minus 4. Remember that this is what z is equal to. Then if we expand it out, we get x squared plus j 2xy minus y squared. Remember, j squared is minus 1. Then minus 4. Grouping the real and imaginary terms, we get x squared minus y squared minus 4. Then plus j 2xy. So that means that u is equal to x squared minus y squared minus 4, and v is equal to 2xy. So we can take day v, day y. So let's do that. Day v, day y is equal to just 2x. Okay, this should equal to day u, day x. So let's compute day u, day x. Day u, day x. That's just equal to 2x as well. Remember that this y squared and this 4 are constants since we're taking a partial derivative. And lo and behold, they are equal. So we can check the same with the other as well. We can take day v, day x. So day v, day x is equal to 2y. Right, we can easily see that. And now we have to compute minus day u, day y. So minus day u, day y. So that's minus and day u, day y. So we have, well, that would be a constant, so 0. And then that would also be a constant. So we just have minus 2y. And that gives us plus 2y. We can see that that and that is equal, and that is equal. So this Cauchy-Riemann equations is actually what we use to establish if the derivative is unique. So if they're not the same, obviously it means that we're going to have a problem. We're going to have an issue there. So these are the two key things. Does the derivative exist, and is the derivative unique? So tied in with the fact if the derivative exists, we're considering an analytical function, also called a regular function. And to establish if the derivative is unique, then we're looking at the Cauchy-Riemann equations. Hi there. In this video, we're going to talk about harmonic functions in the context of complex variables. You would have seen in your study of multivariable calculus that you can have a function of two variables x and y. It could equal to something, for example, x squared minus y squared. If we take the derivative, that's the second derivative of f with respect to x, and we take the second derivative of this function with respect to y, and if we add them together, then we get 0. Okay, so this is called Laplace's equation. In this instance here, we can see that the first derivative, day f, day x, is equal to 2x, and the derivative with respect to y, day f, day y, is equal to minus 2y. And then we take the second derivative with respect to x, and we see that it's 2. And we take the second derivative with respect to y, and we see that's minus 2. And of course, if we add them together, the 2 and then the minus 2 added together give us 0. Okay, so that's Laplace's equation. So when a function has a Laplace's equation applied to it, it's called a harmonic function. So in this instance here, f is a harmonic function because this constraint, this condition, Laplace's equation is there. So how does this apply to the complex plane, and what does this have to do with complex variables? So we have seen thus far that we have a complex variable w, and it's equal to u plus jv, the real and imaginary parts. And we also saw that both u and v are functions of x and y. So this is the kicker, right? So if w is an analytic function, so we spoke about what analytic functions are in the last video. So if W is analytic, then U and V are harmonic functions. We can actually show that. So if W is if W is an analytic function, then U and V are harmonic. So we can prove that both U and V are harmonic by using the Cauchy-Riemann equations, which we had derived in the last video. So if we recall what those equations are, it's that day V, day Y, that's day V, day Y, is equal to day U, day X. That's the first equation. If we find the derivative of both sides with respect to Y, so we have day V squared and day Y squared, that's equal to day U, day X, and then day Y. So the other equation in the Cauchy-Riemann set is that day V, day X is equal to minus day U, day Y. So if we find this derivative with respect to X on the left-hand side, so we get day V squared, day X squared equal to, okay, let me just write the minus on the other side and make that positive. So we have day U, day Y, day X. And what do we know about mixed partials? We know that mixed partials are equal. So that is equal to that, okay? So if these two are equal, then what's on the left-hand sides should also be equal. So what that means is that day squared V, day Y squared is equal to minus day V squared, day X squared. So of course this implies that day squared V, day X squared plus day V squared, day Y squared is equal to 0. So we have shown that V is actually a harmonic function. So we can use the Cauchy-Riemann equations to also show the same thing about U. So all we would do is we would take U with respect to X. So let's do that. So if we take U with respect to X, then we have day U squared, okay, then day X squared, that's the right-hand side, here on the top. And now we do the same thing with the other side of the equation. Then we get day V, day Y, day X. And then applying the other equation, we have minus day U squared, day Y squared. And that's now equal to day V, day X, day Y. So these mixed partials must be equal. So the other side is equal as well. So that means that day squared U with respect to X and the second derivative with respect to Y is equal to 0. So we have derived it in the exact same way. We can show this in a basic illustration. If we have W is equal to Z squared minus 4. We have looked at this example several times now. So if we wanted to prove that this is a harmonic function, what we would actually do is we would firstly gather all the expressions in terms of U and V. So we would have X plus JY. This is the definition of Z. We've substituted Z. We expand that out. So we have X squared plus J 2XY minus Y squared minus 4. We gather the expressions. So we have X squared minus Y squared minus 4. Then we have plus J 2XY. So that means that U, that's the first part of the expression, is equal to X squared minus Y squared minus 4. And V is equal to 2XY. So day U, day X is simply equal to 2x. The rest are treated as constants. And then the second derivative of U with respect to X is equal to 2. So we do the same thing with V. Day V, day X is equal to 2y. Remember that X is treated as the variable. And day V, second derivative with respect to X is equal to 0. Remember that, Y is treated as a constant. So this entire thing is a constant, therefore it's equal to 0. So we can find the same derivatives with respect to Y. So we have day U, day Y, okay, here. So we see that this is minus 2y. And the derivative, second derivative with respect to Y is equal to minus 2. we can immediately see that 2 minus 2 gives us 0. Remember that we have day squared u day x squared and day squared u day y squared. So the sum of this 2 should actually equal to 0. So in the same way here, we can take day v with respect to y, and we can see that this gives us 2x, and then we find the second derivative, day squared v, day y squared, and this gives us 0. Remember that x is treated as a constant, so of course 0 minus 0 just gives us 0. So we have shown that for this particular example, that z squared minus 4, we know that it's an analytic function. We showed that in the last video, and we can see that since it is an analytic function, the second derivative with respect to y of both u and v give us 0, proving that both these are harmonic functions. Okay. So in this video, we're going to be talking about how we integrate in the complex plane. So we have said so far that this complex variable z is x plus jy. If we have to consider a differential change in z, then we have dz is equal to dx plus j dy. Now we have a function that depends on z. We have a function of z, and that we also saw is split into two parts, u, the real part, which is a function of x and y, and the imaginary part v, which is also a function of f and y. So if we are now integrating in the complex plane, okay, we are integrating this function of z with respect to z, okay, fz dz. But what does this integral actually look like? In fact, what kind of integral is this? So let's try to understand this a bit further by substituting in f of z and dz inside this equation. So if we do that, what we get is u plus jv, that's what f of z is, and we have dz, which is dx plus j dy. If we now expand this out, what we get is u dx, that's the first term, then we have u times j dy, so we have j, then we have u, then we have dy, and proceeding in that manner, we have plus j v dx, and lastly j times j is minus 1, so we have minus v dy. So if we group these expressions out, we have the integral, that's if we group it in terms of the real and imaginary parts. So we have u dx minus v dy, then we have plus j, and what's left is u dy plus v dx. So if we try to understand this graphically, what are we trying to understand? So let's look at it. We have our xy plane, or rather the x and y axis and the z plane. We have 2 points, that's A and B, and we have some curve that joins A and B. And each one of these points along this curve, okay, we'll call that curve C, will have some kind of value of z. So there's a value of z along each point of this curve. And each value of z, each point z, will have a corresponding point f of z. So what does this mean? We are adding, right? We are summing each point f of z for each value of z. So what this actually tells us is that we are taking a line integral. So we covered line integrals in multivariable calculus, and the videos are available in that playlist. So you can go and revise that if you want. But just a quick revision here of what a line integral is. And the way I had explained it at the time was that we have a roller coaster. We have the top of the roller coaster, we have the bottom of the roller coaster, and we isolate a single point along that roller coaster, and we know that there's the force of gravity, F of g, acting along that roller coaster, and we can split it up into two components, right? We have that one component like that, and we have this other component like that. So we'll call that component Fs. Now we want to try and understand what is the work done by this roller coaster as it moves, from this high point to this low point. So we know that work done in general, we'll call it W, is equal to force times distance, okay? Force times distance. So there is a small change, delta S, so that's our distance, and we have a force acting. So we have F delta S, that's our work done. But if we wanted to find the work done between A and B, that's A and B, then we have to sum up this entire thing between A and B. So we have to add up f of s along this entire length. So we can split now f of s into two parts, okay? So there's fs delta s. We can say that's like moving, firstly, q dy, okay, and then p dx. So we split up this fs delta s into two parts, dy and dx. Okay? We have just changed the path and broken up the force into p and q like that. So we're saying that fs delta s is equal to p dx plus q dy. So if we wanted the work done, we can replace this sum that's here with actually the integral sign. So what this becomes is that the total work done between A and B is actually this integral of p dx plus q dy. So that was the general form of a line integral between these 2 points. So we have a function, okay, and with each point along that function, we are adding up another function. So that other function is the work done, and we are summing up between these 2 points. So if we think now about the complex plane, okay, we think about the complex plane, what do we have here? We have z and we have f of z. F of z is some other function, and we are summing up f of z between these 2 points. So you can see it's exactly the same. Line integral, we're summing up work done between these 2 points. In the complex plane, we are summing up something else between the 2 points. So that's how it is a line integral. And let's look at what we had just derived. We had seen that we had u dx minus v dy, the real part, and we had u dy plus v dx as the imaginary part. So if you look at these things, we can kind of see that it resembles the form p dx plus q dy. And again here, we have, okay, it's reversed here, but we can see it as p dx and q dy. The same thing. So this is given more credence to the fact as to how we actually see that this entire thing is a line integral. So we can best illustrate this entire thing with a simple example, okay? So we can take a complex function. F of z is equal to z minus j squared. So we want to now evaluate the integral, okay, along something in the z-plane. So we have the z-plane, and we have x and y, and we have 2 points, A, maybe that could be the origin, and we have another point, B. So B is here, and we have a line joining these 2 points. So B would be the point 1 plus j2. So it has a real part 1 and an imaginary part 2. Okay, 1, 2, that's how we plot it. So we want to now integrate f of z, the function z, between these 2 points in the z-plane. So what we're doing is we want to integrate, let's call this curve C. We are integrating along C of f of z dz. So the first thing that we need to do is find u and v, okay? So essentially what we're going to do is we're going to use this expression that we had just derived. So this is what the integral is. So that's what the integral is. And perhaps we can just write it out. So what this is equal to is the line integral of u dx minus v dy plus j v dx plus u dy. So let's find u and v. So there's our function here. All we do is we substitute in terms of z. So we have f of z is now equal to, z is equal to x plus jy. So we have x plus jy, and also we have this minus j, and this entire thing is squared. So how do we go about actually doing this? It's quite straightforward. So we have x squared. Then we can combine this thing and bring out j as a common factor. So let's just write that. So we have j into y minus 1. So now we are squaring that. So the next part is going to be x times the second term multiplied by 2. So we have 2, or rather let's put the j in front, 2x into y minus 1. And then lastly we're going to have j squared, that's going to give us just minus 1. Then we have y minus 1 squared. So that is y squared minus 2y. And then, okay, so we have minus in front because of the j, and we have minus here, so that's going to become a plus. And lastly, we have minus 1 squared, which is 1. 1 times minus 1 gives us minus 1. So now we can group these terms as we usually do. So we get x squared, then minus y squared, plus 2y, minus 1. And then we have j. If we expand that out, we get 2xy minus 2x. So this is what u is equal to. So this part is u, and that's what v is equal to. So we have already described this, derived this expression, and all we need to do is just apply it. So we can take it and we can bring it down here. So we can just write this right-hand side of this equation, and it's the integral, and we're integrating along c of u dx. So this is what u is equal to. So u is equal to x squared minus y squared plus 2y minus 1, and then we have dx, then we have minus v, and v is equal to 2xy minus 2x. So we have 2xy minus 2x, and this is multiplied by dy. Then we have plus. Let's group it like that. Then we have plus j, and we have v dx. Okay, we have v dx, and v we saw is 2xy minus 2x, and we multiply that by dx, and then lastly we have plus u, and u is this entire thing, so it's x squared minus y squared plus 2y minus 1, and that is multiplied by dy. Okay, so how do we integrate this long thing? And we have dx, we have dy, and we have y, and what are we integrating here? So we are integrating along this path. Okay, so let's not forget that, this path. And do we have a relationship between x and y? Yes, we do. It's a straight line. We can clearly see that y is equal to 2x, and that means that dy is simply equal to 2 dx. So that's the relationship between dx and dy and all of these things. So to evaluate this integral that we have just seen now, all we need to do is eliminate y and dx. So wherever we see y, we substitute in 2x, and wherever we see dy, we simply substitute 2 dx, because that's what we have just seen here on the top. So if we do that, we're integrating now, and we're putting everything in terms of x, and we can see that x goes from 0 to 1. Okay, so our integration bounds is from 0 to 1. So we have 0 to 1, and we substitute in all of these things, and when we do that, what we get is x squared, and then we have y squared, so 2x squared gives us minus 4x squared. Then we have 2 times y, or 2 times 2x, which gives us 4x, and then minus 1. and we have this dx here, and then we have minus 2xy, or 2x times 2x, which is 4x squared. Then we have minus 2x, and then dy, and then dy we know is 2dx. And then plus j, 2xy, 2x times 2x is 4x squared, minus 2x dx. And then lastly, we have again what u is. So we just repeat this expression for u that's entirely in terms of x. So it would be just x squared minus 4x squared plus 4x minus 1. And then evaluated with respect to dx. So this entire thing is just a basic integral to do. All we just do is, all we need to do is simply just bring everything in terms of x, bring everything in terms of dx, and combine all this expression and simplify, and then just integrate between 0 and 1. This is a very elementary thing to do, so I don't think it's required to show all of these steps. It's something that can be done on your own. And when you do that, you discover that this entire integral becomes 1 over 3 into minus 2 plus j. So when you group all these terms together, when you integrate, when you put in the boundaries and all of that, you find that you get this final expression. So please attempt that. In this video here, we covered a bit of content and we showed how to integrate in the complex plane. It's called a contour integration. And we see that we get that by forming a line integral. So integration in the complex plane is a line integral. So that's where the word contour comes from. It's a contour integration. And we just revised what a line integral is, and we saw that it becomes this equation. Integral u dx minus v dy, the real part, and the imaginary part, u dy plus v dx. And all we need to do is take our expression that's in terms of z, and what we do is we put everything in terms of x and y, and we group everything in terms of u and v, and we just apply this equation that is easily derived, and we get our final integral. We see that that value of the line integral in the complex plane is 1 over 3 into minus 2 plus j. In this video, we're going to talk about the Cauchy-Goursat Theorem, also known as Cauchy's integral theorem. We commenced by writing the integral of a complex variable as we had done in the last video. We had some complex function of z equal to u plus jv, with the real and imaginary parts being u and v, both functions of z. And we had a differential change in the complex variable z made up of differential parts dx and dy. We then saw when we write the integral of fz dz, we have to combine these things. And we write the integral of fz, we substitute in u plus jv, and we have dz, and we plug in dz, that's dx plus j dy. And once we expand all of this out and we combine some of the terms, what we get is the line integral around a certain path, u dx minus v dy plus j v dx plus u dy. So what we have considered so far is just integration around one path. We have 2 points, maybe A and B, and we have integrated along one path from A to B, and we had seen that this was a line integral. So now we're considering the case where we're going to integrate along a closed path, okay? A closed path. So that means we integrate fz dz firstly from A to B, and then from B back to A. So what does this look like? Well, we use our same line integral that we had derived, and all we now consider is the integral around a closed path. So what we're saying is we're going to evaluate this entire real part, u dx minus v dy, as the line integral around this closed path, and we're going to do the same thing with this imaginary part. So this line integral of fz dz is actually just equal to this line integral of this real part u dx plus, minus v dy, and then plus j, and this integral circulation of v dx plus u dy. So that is it. That is it. So what's the next step? The next step is that we are going to take this line integral that we have just derived around this closed path for both this real and imaginary, and what we're going to do is apply Green's theorem to it. So if you want to revise what Green's theorem is, you can go back to the previous videos in multivariable calculus and revise that. So I had done videos on this. But what Green's theorem is that it says if we have the integral around a closed path C, and it's made up of p dx plus q dy, what we can say that is that it's also equal to a double integral around this region, the area between this inside this closed path, of dq dx minus dp dy. And since it's a double integral, we'll have dx dy. So what Green's theorem allows us to do is take a line integral and convert it into an area integral. So why we use that is that sometimes it's easier to evaluate the line integral, and sometimes it's easier to evaluate the double integral. So this allows us to go between the two. So what we can do is now we can apply Green's theorem to this real part of this integral and to this imaginary part of this integral. So let's do that. Let's just zoom back in. So we have the line integral around the closed path of u dx minus v dy. And if we apply Green's theorem, we're saying it's the double integral around some region of dq dx. So here q is equal to minus v. Okay, rather let's write p first. So here p is equal to u p dx, and q is equal to minus v. So we have dq dx, so we have minus dv dx, since that's what q is equal to. So we have minus dv dx, and then we have minus dp dy. So p is u, so we have du dy and dx dy. So let's write this for this other integral as well. So we have v dx plus u dy, line integral closed path of v dx plus u dy, and this is equal to this double integral around this closed region of p dx. So here p is equal to v and q is equal to u. So we have dq dx, so we have dv dx minus dp dy, so we have minus dv dy. Sorry, this should be a u here. So dq dx and q is equal to u, so we have du dx, and then dp dy and p is equal to v, so we have dv dy. So what are we going to do with this? What is the whole point of this? How does this help us? Well, this double integrals actually become zero, okay? How do they become zero? Well, we can see that they are zero if we consider the Cauchy-Riemann equations. So we had derived these equations in one of the previous videos in the series. So I encourage you to go and have a look at how they are derived, but we're just going to use them here. So the Cauchy-Riemann equations said that du dx is equal to dv dy. And the second equation was that dv dx is equal to minus du dy. So if we bring this dv dy to the other side, we get du dx minus dv dy equal to 0. And if we do the same to the other side, for the second equation, we take dv dx to the other side, we're going to get minus du dy minus dv dx is equal to 0. So let's look at this. Du dx minus dv dy. What do we have in this double integral? Du dx minus dv dy. So we can see that this thing is 0. So if this thing is 0, this entire double integral is 0. And it's the same here. We have minus dv dx minus dv dx minus du dy. So quite perfectly, this whole thing all simplifies to 0. So what does this mean? It means that if we look at this line integral of fz dz, if this part is equal to 0 and that part is equal to 0, which is what we have just shown, it must mean that this line integral is equal to 0. We can write that as a result. So this result that we have seen now is that if we take the line integral, in other words, around a closed path, the line integral around a closed path of c of some function z dz, and it's an analytic function, also known as a regular function, which we discussed also in previous videos, we see that it's equal to 0. So this is what is called the Cauchy-Goursat theorem. Also known as Cauchy's integral theorem. We can also apply this to a simple example just to see it illustrated. So let's just take a path. There we have A and we have B. And B is the point 1 plus j0. And then we can also have C. And C is the point 1 plus j. So let's consider a path where we go from A to B, and then B to C, and then C to A. So what function are we considering this for? We can say that maybe f of z is equal to z squared. And what we want to evaluate is this line integral around this closed path of fz dz. So this line integral around this whole curve C, or rather this entire path C of fz dz, so that's going to equal to the integral from A to B, fz dz, then plus integral from B to C, fz dz, and then finally the integral from C to A of fz dz. So how we're going to apply it is by using this line integral that we had derived earlier in terms of u and v. So we have this integral around C closed path of f of z dz. Let's just write it out again. This is equal to this line integral around this closed path of u dx minus v dy plus j line integral closed path f of z dz. And then we're going to apply this to AB, BC, and CA. So let's just find what u and v are. So we have f is equal to z squared, so let's write that here. So we have f of z equal to z squared. So this means that it's equal to x plus jy squared, because that's what z is. So then that gives us x squared plus j 2xy minus y squared. So what this means is that u is equal to, if we gather everything across here, so we have x squared minus y squared, we gather the real part, and then we have plus j 2xy. So that's what v is. So that's what u is, and that's what v is. So u is equal to x squared minus y squared, and v is equal to 2xy. So we can substitute all of these things inside this equation. Okay, so this is what we actually need. So we have the integral around c of u dx. So u is equal to x squared minus y squared times dx, then minus v is 2xy dy, then we have plus j, and we have so we can put in what this integral was equal to as well, and that was equal to v dx plus u dy. So let's just put that in. So that's v dx plus u dy. So v, we have 2xy times dx, and we have u, that's x squared minus y squared dy. So let's apply this to the path AB. We can see that for AB, well, there's basically no change in y, and of course y is equal to 0 here. So that's the first thing we can note. We can note that y is equal to 0. So this implies that dy is also equal to 0. What this means, if we now apply this for AB, we take line integral of AB of fz dz. That's going to equal to, well, firstly, this entire term will disappear because dy is equal to 0, and so will this term because y is equal to 0. So what that means is that we're going to integrate from 0 to 1. That's our first boundary of integration for x. And we're going to have x squared minus y squared, y is equal to 0. So all we're going to have is x squared dx, and dy is equal to 0, y is equal to 0, and dy is equal to 0. So this is the only term that we have. And if we integrate that, we're going to get 1 over 3 x cubed, 0 to 1, and that gives us 1 over 3. So we can now do it for b to c of fz dz. And that's going to essentially also be the integral from 0 to 1. But now what we're going to do is we're going to consider it, let's write it. So before we go there, let's note some points about the path BC. So for BC, we see that x is equal to 1, and that means that there's also no change in x at this point. So for BC, it means that x is equal to 1, and therefore dx is equal to 0. So if we consider line integral for BC, we have to integrate with respect to y. So y goes from 0 to 1. So dx is equal to 0, so that term won't be there. So let's consider the second term. We have minus 2xy. Y is going from 0 to 1, and we have minus 2, well, x is equal to 1. So we have essentially minus 2y, then dy, then plus j. Again, y is going from 0 to 1. Dx is equal to 0, so that's not going to be there. And then we have x squared minus y squared, x is equal to 1. So we have 1 minus y squared dy. And if we continue with this, then we see that we get minus y squared, if we integrate minus 2y, going from 0 to 1, and then plus j. Integral of 1 is just y, and integral of y squared is minus 1 over 3 y cubed. Also going from 0 to 1, and if we substitute in 0 and 1, then what we get is minus 1 plus j. Then we have 1 minus 1 over 3. So 1 minus 1 over 3 is just 2 over 3. So that's what the integral of BC is equal to. And then lastly, we need to do the third part. That's from C to A. So what are some observations about C to A? Okay, we're going along the line y is equal to x. Okay, that's 0, that's 1, and both x and y are equal to 1 here. So the equation of the line is y is equal to x. So y is equal to x, then that means that dy is equal to dx. So we can carry on with this expression, and we can write it. So we substitute in dx for dy, and we substitute x in terms of y here, and we can proceed with this integration. So if we do that, we get the integral CA fz dz. So that's going to equal to integral, well, it's going from 1 to 0. So what we can do is we can take the integral from 0 to 1 and reverse it. So instead of writing 1 to 0, we just write minus 0 to 1. So we have x squared minus y squared, y is equal to x. So x squared minus x squared is equal to 0, so that term won't be there. Then we have minus 2xy, so y is equal to x, so we have x times x, that's going to give us x squared, and then dy is going to equal to dx. So we'll have minus 2x squared here, and then with regards to the j part of it, then we have y is equal to x again here, so we have x times x, that's going to give us x squared, and x squared minus y squared is going to give us 0. So that term will come out, and that term will come out, and then we substitute for x and y and dy here. And when we do that, what we get is the integral of 2x squared dx plus j, again reversing the order of integration, 0 to 1 minus 2x squared dx. Sorry, there's a minus here as well. So the minus and the minus is just going to give us a plus. We can just remove both the minuses. So proceeding with this integration, we have 2 over 3 x cubed, 0 to 1, and then minus j 2 over 3 x cubed, 0 to 1. So what we then left with is 2 over 3 minus j times 2 over 3. So if we now add this integrals of a to b plus integral from b to c, and then lastly from c to a, then what we're going to get is, well, a to b was 1 over 3, and then b to c was minus 1 minus j2 over 3, and finally CA was 2 over 3 minus j2 over 3. So substituting all of that in, we get 1 over 3, then minus 1 plus j2 over 3, and then lastly plus 2 over 3 minus j2 over 3. So 1 over 3 plus 2 over 3 is 1. 1 minus 1 is 0. And then we have 2 over 3j minus 2 over 3j. That's also going to give us 0. So we can see that this whole thing becomes 0. So we have shown that if we have an analytic function, we integrate fz dz around a closed path, then we get 0. So this is what the Cauchy-Goursat theorem is, also known as Cauchy's integral formula. or in Cauchy's integral theorem. In this video, we're going to talk about conformal mapping. So conformal mapping is actually a very important application of complex analysis. What people use it for is that they take extremely difficult geometries with very complex shapes and whatnot, and they transform it using transformation equations into shapes that look much easier but preserve some of the essential information about the original shape. For example, if you look at the wing or the airfoil on an airplane, you can see that it's of a certain shape, and if you were to investigate the fluid mechanics of that shape, you would see that the boundary conditions of the differential equations are actually influenced by the shape. So what we can do is that we can transform some of these shapes in many different fields of engineering to be able to analyze the information and obtain simpler equations by doing some transformation or mapping between the different complex planes. So there's a reason why we need to check if a mapping or a transformation between different planes obeys what's called a conformal restriction, rather not a restriction, but rather a kind of condition in which some information is preserved. And we can start off by looking at lines. So we have our normal z plane with the x and y coordinates, and we have two lines. That's A, B, and then maybe AC here. If a mapping from the z-plane to the w-plane is said to be conformal, then what we need to ensure is that the angles between these transformations is the same. So between AB and AC, there's an angle alpha, and now this is mapped into the w-plane with its coordinate systems being u and v, and now we have A prime here, and then we have B prime here, and then we have C prime. So now these angles must also be the same here. So the angle there should be alpha. So the reason for this is, even though we may transform geometries into a complex shape into a simple shape, we want some essential information like angles to be the same. So for a transformation to be conformal, then what it has to ensure is that the angle, in this case alpha, is the same in both the W and Z planes. It's also important to note that the angle should be in the same direction. So the direction is also important. So the angle is in the same direction. So in this case here, it was measured counterclockwise. We can see we measured alpha to be counterclockwise from AB to AC, and the same is the case here as well. So if we want to now extend this to curves, you can see again we have our z-plane with x and y, and our w-plane. We have the w-plane here with u and v. So what we need to check are the tangents. So we have some intersecting points. Okay, we have a tangent associated with the one curve. So let's call that C1. And we have another curve, C2. And that curve will also have a tangent. So it would look something like that. So we can call this maybe tangent 1, and we can call this tangent 2. So if we now look at the transformation, then what information needs to be preserved is also in terms of the tangents. So we'll have maybe call this tangent 1 prime, and we can call that tangent 2 prime. So the tangents here will have a certain angle. We can call that alpha as well. So in the case with curves, this angle alpha should also be the same in both instances. So for curves, we just need to check the angle alpha between these different curves in the transformation and ensure that they are the same. So what we also associate with tangents is the derivative. Okay, so if we're saying that the angle should be the same, what happens if the derivative is equal to 0? What happens now if we have tangents that are equal to 0? So there's the one tangent like that, and there's maybe another tangent like that. So both of these tangents are 0. So does that mean anything? They are technically parallel to each other and the angle between them is 0. So does that mean anything? So the answer to that is that no, it doesn't mean anything. If the derivative, that is f prime z, is equal to 0, then what this means is that it's not conformal. So if we are checking if a certain mapping is conformal, then we also have to check f prime z and ensure that this is the case. We could have a certain function of z, for example, z is equal to 1. So this is actually a circle. So that's a circle. Because we're talking about the magnitude of z, that's x plus minus j, right, equal to 1. Unit circle. Now we can have a transformation, w is equal to z plus 4 over z. So that's our transformation now. So the question is this mapping conformal? How would we do that? Well, the first thing that we need to see is that there is one particular point where z is not defined, and that's where z is equal to 0. We can see that if we substitute 0 in here, we have an undefined value of w. So when we have that undefined value, that we would call a singularity. So we have a singularity at z is equal to 0 because it produces an undefined value of w. So now we can also check critical points. Remember that earlier we spoke about we need to check f prime z is equal to 0. So that indicates critical points. So we have to check critical points. So all we need to do is simply find dw dz. And this function is analytic everywhere except for z is equal to 0. So we find the derivative. We find that it is 1 minus 4 over z squared. And if we set this equal to 0, then we find that z is equal to plus minus 2. So this would be the critical points. So what we are saying here that the function is conformal, right? This is a conformal mapping except at plus minus 2. So it's conformal except for everywhere besides the critical points. So this particular type of transformation forms part of what is actually called the Joukowsky Transformation. So what this is that it takes a circle, a unit circle, as we had shown earlier, z is equal to 1. Okay, that's roughly like a circle, unit circle. And what it produces is this z plus 4 over z. So if we were to actually plot this out or determine analytically what the shape looks like, we find that it's actually a ellipse. Something like that. So we made a circle into an ellipse. So with a little bit more work, a little bit more manipulation of this transformation equation, we can actually play around with this shape a bit more and make this shape a bit different. Maybe something like that. The point is that we can make this shape more and more look like the wing of an airplane or an airfoil. So this is how this kind of mapping or transformation is actually applied. And we find that it actually works besides the points plus minus 2. So the key takeaway from this video is that conformal mappings are quite important because we can use it to represent a great deal of different geometries and make them simpler to work with. But the key thing here is that we have to check that the angle between lines, geometries are the same. And also we have to ensure that when it comes to curves, we have to check for singularities and critical points. We have seen thus far that an important application of complex analysis is the ability to take complex geometries and complicated shapes and convert them into something similar by transforming it into a different plane. So this video focuses on a specific type of transformation, that is the Schwarz-Christoffel transformation. So what it does is that it maps a polygon region in the z-plane onto the upper half of the w-plane. So if in the z-plane we have some kind of complex figure like this, and it has some kind of region that's very difficult to work with and describe equations and boundary conditions and so forth, we can take this particular complicated region and we can say that it forms entirely the upper half of the w-plane. So this entire little region inside this polygon becomes essentially the entire plane of the w-plane. That's the top half of it. The second thing about the Schwarz-Christoffel transformation is that it transforms the boundary, and perhaps this is a bit more useful depending on the circumstance. So what it does is that it converts the polygon boundary into a single line, the real axis of the w-plane. So you can take all these different lines and all of this complicated shape, and instead of having a complicated boundary like that, we can transform that entire boundary. We can cut it and we can spread it out. We for example, cut it and open it out, and it becomes one single line that is on the u-axis, the real axis. So remember that this is the w-plane and this is the z-plane. And we can now take this boundary and open it out and put it on the real axis of the w-plane. So instead of many different shapes, we just have a line. So this video is going to illustrate how to go about doing this. So this is perhaps easiest illustrated to start off with by a simplistic example. Here we have a certain kind of boundary in the z-plane. We have a vertical line, we have a horizontal line, and another vertical line. And there is a region. Yeah, so we're going to take this region and we're going to show how it is the entire upper half of the w-plane and how these different points are simply just points on the real axis of the w-plane, and this entire different line can just be spread out into one single line on the real axis. So what we're going to do is we're going to apply a transformation equation to map these lines and this region into the w-plane. And that transformation equation is that w is equal to minus cos pi z over a. So the question is, how did we know to take this particular transformation equation? So this is what we need to actually come up with, right? We need to find the equation that will transform these lines and this region into what we want. So there is a procedure to follow to find out this particular transformation equation, and we will illustrate that just now, but first we will actually show how this maps onto the w-plane. So we know that z is equal to x plus jy, and we will substitute that in. So when we do that, we get pi into x plus jy, pi into x plus jy, and then divided by a. So we have kind of a double angle here, or rather two angles added together, and you would remember from your trigonometric identities that cos a plus b is equal to cos a cos b minus sin a sin b. So we can substitute that in and apply this trigonometric identity. Here is our a and here is our b. So this means that w is equal to minus cos, firstly pi x over a, then cos of b, and b is jy over a times pi. So we have j, then pi, then we have y divided by a, then minus sine pi x over a, and then sine b, that's sine j pi y over a. So now we can apply some other identities here. We can get rid of this complex number actually. If we remember our rules or our identities regarding hyperbolic functions, then we would recall that cos of j theta is actually equal to cosh. That's cos hyperbolic of theta. And also we can remember that sine of j theta is equal to j sine hyperbolic or sine theta. And we can now apply these things. And when we do that, we get that w is equal to, we can apply out that minus, so we get minus cos pi x over a. Then we can apply now hyperbolic function. So this will give us cosh pi y over a. Then we have minus, and a minus gives us a plus. So that sine pi x over a remains the same. And then we have hyperbolic function, but remember that j is outside, so we have to write the j in front. So we have sine hyperbolic pi y over a. So if we analyze this, we see that we have a real part, an imaginary part. So that means that u, remember that w is equal to u plus jv. So this first part is u, so we can write that as u. So u is equal to minus cos pi x over a, cosh hyperbolic pi y over a. And also we can see that v, this imaginary part, is equal to sine pi x over a times sine hyperbolic pi y over a. So what we can do is we can now start converting some of these points between the different planes. So let's do it with B and C. So we can see that B is just at the origin and C has a coordinate that's x value a and y coordinate 0. So let's do that. So at B, we can see that x is equal to 0. This is literally the point of origin. And y is equal to 0 as well. So what that means is that when we map it into the w plane, B prime, we get that u is equal to minus 1. We get that by substituting 0 for x and y inside this equation for u. So x is equal to 0, so we have cos of 0. Cos of 0 is minus 1. So we have minus times cosh pi y over a. So we also need to perhaps remember that cosh of 0 is equal to 1 and sinh of 0 is equal to 0. So in any case, we have cosh of 0, so that gives us 1. So we have minus 1 and 1, and that's how we get that u is equal to minus 1. And of course, we can see that v is equal to 0 because sine of 0 is just 0. So this entire term is going to be 0. And this is what we want, right? This is what we want. We said that in terms of our mapped variables, we want only the upper half of the plane, okay? And we want this entire boundary to simply be on the real axis. So we want v is equal to 0. So this is u and this is v. We don't want any values of v in terms of these boundaries. We only want it to be on the real axis. So this is something that we are specifically targeting. We can now do this for C. At C, x is equal to a and y is equal to 0. So what this means when we map it is that u is equal to, we substitute in a here, so we have pi a over a. So the a's will cancel off and we're left with minus cos of pi, and cos of pi, just to remember, is equal to minus 1. So this term gives us minus 1 and cosh of 0 is 1. So minus times minus 1 gives us plus 1, and 1 times 1 is 1. So u is equal to 1. And if we look at here, we have a sine hyperbolic. Okay, this is a hyperbolic function. Sine hyperbolic of 0 and sine hyperbolic 0 is 0. So this entire thing is going to be 0. Again, this is what we want. We want v to equal 0. So we have our 2 points. We have b prime and c prime, and they are at -1 and 1. So we can plot that. So there's b and there's c, and now we have -1 and +1, and this is where b prime is, and this is where c prime is. So now at this point, what we need to do is map these lines, AB and DC. So when we do that, we can start off with AB. We can see that x is equal to 0. So let's just have a look at it again. So here for the line AB, we can see that x is equal to 0, and y is definitely there. We can see that we have decreasing values of y. So y is coming from infinity and it's coming to 0. Here between BC, we can see that y is equal to 0 and x is actually going from 0 towards a. So x is going from 0 to a. And then lastly, we have CD. So at CD, we can see that x is equal to a, and obviously it's increasing towards infinity. So y goes from 0 to infinity. So we can just complete that for AB, x is equal to 0. So since x is equal to 0, we can substitute it in for the value of u and v. So when x is equal to 0, we have cos of 0, which is -1. So we can see that u is equal to minus cos pi y over a. And of course, v is equal to 0 because we have sine of 0 in v, and then sine of 0 is of course 0. So we can see here that y is going from infinity to 0, or y is between 0 and infinity. And when we substitute that in, okay, we can substitute in 0. We have cos of 0. Cos of 0 is 1, so we have -1. So that tells us our upper bound is -1. And if we put in infinity, we have cos infinity, which is minus infinity, because of the minus in the front. So u goes from minus infinity to -1. So what that means is that if we were to plot that on this axis, we are saying that u is going from minus infinity to -1. So on this line, it looks like that. So we have a prime to b prime. So this line AB transforms to a prime to b prime, that is minus infinity to -1. So now we can do b prime to c, or rather b to c. And when we do that, so we have b to c, and at b to c, we have y is equal to 0. So what that implies, y is equal to 0. And what that implies is that u is equal to minus cos pi x over a. If we just substitute in 0 here, we can see that cos of 0 is 1, so we're left with just the term with the minus cos. And of course, v is equal to 0. And in terms of x, so x that we can see is going from 0 and is stopping at a. So remember at the line BC, x is going from 0 to a. X is going from 0 to a. So we convert that in terms of u and v. So what that means, if we substitute in 0, we have cos of 0, which is -1. And if we substitute in a over a is 1, so we have minus cos pi, which gives us 1. So that means that BC is actually going, transforms to being between -1 and 1 in terms of u. We can actually draw that on our plot. And when we do that, we see that it goes from, u is going from -1 to 1. So that's B prime C. So we can see we have mapped these two vertical lines that are at 90 degrees into one single line. And then lastly, we just have C to D. So let's just see how that is mapped. We can pretty much anticipate that it's going to be also on the real axis because that's what we want. So we intuitively going to see that it's going to go like that. So let's just see that in terms of the numbers. So we have C to D. So C to D. So at CD, x is equal to A. So what that implies when we substitute in A, so we have A over A, that gives us minus cos pi. So this entire thing is going to give us 1. And all we're left with is cosh of pi y over A. Remember that minus cos pi is minus 1. So minus times minus 1 gives us plus 1. So we're just left with this cosh. So we have u is equal to cosh of pi y over A. So in terms of u, well, let's look at the boundary for y. So y is going from 0 to infinity. Y is going from 0 to infinity. So in terms of u is going from 1 to infinity. If we put in 0 here, we have cosh of 0. Cosh of 0 is 1. If we put in infinity, we have cosh of infinity, which is just infinity. We can see u goes from 1 to infinity. So that is exactly what we see. Goes from 1 to infinity. So that's d prime here. So what have we seen? We have seen that we have mapped this entire boundary. We have kind of spread it out and we have put it into one single line. So that has made our work actually much easier. Instead of having a complex geometry or something in which, in this instance, it's more of a simple example. But we can see that we have taken something that was a bit more difficult to work with previously and just made it into a single line. So in terms of the region, so the region is the entire upper half of the W plane. So in this example, what we have done is use the transformation equation, W is equal to minus cos pi z over A. So the original question was, how did we know to use this particular transformation equation? So that's what we're going to see now. If we have a generic polygon in the Z plane with edges AB, BC, and CD, and these points labeled as they are in this picture, and the angles between the different lines, for example, alpha 1 is between A and B, alpha 2 is between B and C, alpha 3, C and D, and so on like that. So what we want to do is map or transform these points A, B, C, D onto the real axis, the u-axis of the W plane. That means their corresponding maps A prime, B prime, C prime, and D prime have points U1, U2, U3, and U4. So that's what we want to achieve. So we're not going to actually derive this actual transformation. We're just going to show the method as to how it's actually done. So what we want, W over dz, so this is just a method. The derivative of W with respect to Z is equal to some constant A into W minus U1, that's U1 here, to the power alpha 1, that's this angle between A and B, over pi, alpha 1 over pi, minus 1. Then we have W minus U2 into alpha 2 over pi minus 1 multiplied by W minus U3 into alpha 3 over pi minus 1, and so on, depending on how much of edges that you have. So what we're going to do is integrate this. So when we integrate it, we get that Z, or rather W is equal to the integral. A is a constant, we can bring that out. We have A times the integral of W minus U1 into alpha 1 over pi minus 1 w minus u2 into alpha 2 over pi minus 1. And it carries on like that. It carries on, and the last term will be w minus un to the power alpha n over pi minus 1. And we'll have dw. This is what we're integrating. And then we have a constant of integration, because this is not a definite integral. So we have a and we have b. So let's apply this to our case. So if we go to this example that we had originally done, here we have b and c, and here we have this angle. This angle we can see is 90 degrees. It's 90 degrees. And this is also 90 degrees. So this we can think of alpha 1. So alpha 1 is pi over 2. And this alpha 2 is also pi over 2 radians. So let's do that. We can say that alpha 1 is equal to pi over 2, and alpha 2 is also equal to pi over 2. And at these different points, we had chosen u1 to be minus 1 and u2 to be 1. It was on the real axis. So we can substitute these values inside our expression for dw dz. And when we do that, what we get is dw dz is equal to a into w minus, and a minus gives us a plus. So we have plus 1 to the power pi over 2. Remember, that's what alpha 1 is equal to. And then this is divided by pi. And then we have minus 1. So we put that in. And then we have w minus u2. u2 is equal to 1. So we have w minus 1. Again, same thing. Alpha 2 was pi over 2. So we had pi over 2 divided by pi minus 1. So that pi and that pi will cancel out. Same with the second expression there. So we have half. That's what it gives us. So half minus 1 is minus half. And it's the same thing with this second expression as well. So this is equal to a into w plus 1 to the power minus half into w minus 1 also to the power minus half. So this we can write it as 1 over the square root of w minus 1, w plus 1, and we can see that this is equal to 1 over the square root of w squared minus 1. So this is actually equal to w squared minus 1 to the power minus half. So we have a into w squared minus 1 to the power minus half. We just played around with some of the exponents. So anyway, what we can do is take out minus 1 as a common factor. Okay, we take out minus 1 as a common factor because we want 1 minus w squared to the power minus a half. And you'll see why just now. But because we've taken out this minus 1 and all of that, this constant a changes. We can write a new constant k. So this is what dw dz is equal to. The reason why we have written it like this is because this is now equal to k over the square root of 1 minus w squared. So this is a standard integral. Remember that this here is a derivative, and we are now integrating this because we want w. So if we now find w, so w is equal to this integral of k, let's write it over 2 lines. So we have k over square root of 1 minus w squared. We're integrating this with respect to dw. So what this is a standard integral, right? So this is a standard integral. It means that it's equal to k arc sine w plus I. Sorry, I made an error here. This should have been z. This is z, and it's also z here at the top. So anyway, we have an expression for z. Z is equal to k arc sine w plus I. And what we're now going to do is solve for w. So w is equal to sine z minus I divided by k. So we have to solve for these constants I and k. And to do that, we use these 2 points. Okay, we use B and we use C. So at B, we had z is equal to 0 plus j0. And at C, we had z is equal to a plus j0. So let's just remind ourselves. So here we're talking about B and we're talking about C. So B was just the origin, that's why we had 0, 0. And at A, we have real axis A and no y value. So if we go back down, so we can proceed in this manner. So we had w is equal to sine z minus I over k. So w is equal to actually minus 1. Okay, w is equal to minus 1. Remember that this is the value of u1. u1 is equal to minus 1. Then we had sine 0 minus I divided by k. And then we take arc sine of both sides. So arc sine minus 1 is minus pi over 2. And we get minus I over k. So then what this means is that k times pi, we just cross multiply and express I and k in terms of each other. So k pi is equal to 2i. If we do the same thing at the other side, we have z is equal to 1. This is the value of u2. So u2 is equal to 1. So we have 1 is equal to so this is the expression that we are applying here. So just keep that in mind. So w is equal to that value of u2, so that's equal to 1. And now we have sine z minus I, z was equal to a minus I divided by k. So arc sine 1 is pi over 2, and that's equal to a minus I divided by k. So that means that k times pi is equal to 2a minus 2i. So we can solve for these things, right? So k pi, so that means that 2i is equal to that term. So we have 2i here is equal to 2a minus 2i. So we can just easily solve for I. We see that I is equal to a over 2. Take the 2 pi to the other side. We have 4i is equal to 2a. Divide both sides by 2. So now we have k pi is equal to 2i, so we can bring that here. So that means that k pi is equal to 2 times I, and I is equal to a over 2. So that means that k is actually equal to a over pi. So let's just remind ourselves what w is. W was equal to sine of z minus I over k. So this is equal to sine, we just divide here, z over k minus I over k. And this I over k, let's just do it here, I over k is equal to a over 2, that's what I is equal to, and divided by k. K was a over pi. So this is clearly equal to pi over 2. We have pi over 2. So this term here is pi over 2. So we have sine z over k minus pi over 2. So we're just going to bring this pi over 2 to the front and change the sign. So we have sine of minus pi over 2 minus z over k. So sine of minus the angle is just minus sine of the angle. So we have minus sine pi over 2 minus z over k. So trigonometric identity, sine of 90 minus theta is equal to cos of theta. We use that. So we have minus cos z over k. So we have applied that here. And now this z over k, we can substitute that in. We have minus cos z divided by k, and k we had seen was a over pi. A over pi. That's a divided by pi. And that gives us minus cos pi z over a. And if we look at what our original transformation equation was, okay, so we have just shown it's supposed to be minus cos pi z over a. And let's compare it to what we had used. We go all the way up, then we see that here it is. We can even go more further up. And we had shown it here. This is what we started with. So in summary, what we've illustrated is a certain boundary and how we converted it into a line and also the region. And the second part was showing how we came up with that transformation equation. There was a certain procedure that we had to follow. And this part of the video illustrated that procedure. Hi there. So in this video, we're going to look at how to expand a complex variable to be in terms of a series. That is, we're going to apply the Maclaurin series expansion to a complex variable. So what these series expansions do is that they take a function in general and they convert it into a sum of infinite terms, and those terms are polynomial terms. So the Maclaurin series is actually a specific case of the Taylor series. The Maclaurin series is applied for a value of x where it's near 0. So we would apply the Maclaurin series for where x is near 0. So where x is near 0. So if we were to write out the Maclaurin series expansion, not just yet for a complex variable, even though it's the same thing, the general series expansion is that f of x is equal to, firstly, where f is equal to 0, so we'd substitute 0 in terms of our given function, that would be this term. Then we add to it x, and we multiply it by the first derivative, where x is equal to 0. So we would say x is equal to 0. So we can just write 0 inside here. And then the next term is we would now increase the degree. So x is equal to 1 here, and then it's equal to 2. So we have x squared, and then we multiply it by the second derivative, where x is equal to 0, and we divide by 2 factorial, and 2 factorial is just 2. And then next term, we add x cubed, and we would have the third derivative at 0, and we would divide by 3 factorial. So we can carry on adding terms in this fashion here. And then if we were to extend it to the nth term, then what it would look like is x to the power n. You can see that this is the pattern. 1, 2, 3, and then the nth term is just n. And then we would have the derivative of the nth order at 0 and divided by n factorial. And it would carry on like that. So how do we extend this to a complex variable? We would remember that a complex variable z is made up of an x and a y, and it's in the complex plane and all of that. Well, to extend it to a complex variable, it's exactly the same thing. All we would do is we would substitute x with z. So this entire thing would just become a function of z is merely equal to that function where z is equal to 0. Then we would have z, and then we would have first derivative at 0 plus then z squared, then the function second derivative where z is equal to 0, then divided by 2 factorial, then plus z cubed, and then third derivative with 0, then divided by 3 factorial, and so on. and then the general term would be, of course, z to the power n, and then the nth derivative at 0 and divided by n factorial. So the difference here between a function where z and x, we would remember that there are some complications in terms of how we analyze it. Remember that z may have a singular value. Remember that we would think of the Cauchy-Riemann equations and so on. So we're going to get into whether this expansion is actually valid in the upcoming videos and how we interpret the different points where it might or might not be valid. So just to do this for a single example or a simple example, we could have a function. Let's just say where f of z is equal to 1 plus, or rather 1 minus z to the power minus 1. So we want to expand out this function in terms of the Maclaurin series, and the way we would do that is by now computing these various terms. So we would firstly take where the first term z is equal to 0. So where z is equal to 0, so we'll just write 0 here, and then this is equal to 1 minus 0 to the power minus 1, and this is just equal to 1. And then now we take the first derivative, and this is 1 minus z, 1 minus z to the power minus 2. Minus 1 will come to the front, okay, and we subtract 1. So minus 1 becomes minus 2. And then we take the derivative of the inside function. So we're actually using the chain rule here. So in the front there's minus 1, and then the inside of the function, the derivative is minus 1 as well. So minus 1 of the inside times minus 1 of the outside gives us just a 1 in front. So it's the same thing here. That's how we get this 1 in front. So now if we compute that first derivative at 0, then we would have 1 minus 0 to the power minus 2, and that again gives us 1. Then we find the second derivative, then we would have minus 2, and then times the inside function minus 1, so it just gives us 2 on the outside, so we have 1 minus z to the power minus 3, and that derivative at 0 is equal to 2 into 1 minus 0 to the minus 3, and we can write that as 2 or 2 factorial. So we carry on in this manner. So we have the third derivative at z. So this minus 3 times this 2 gives us minus 6. Then minus 6 times the derivative of the inside, which is minus 1, gives us 6. Minus 3 times minus 3 times 2 times minus 1. So that 6 we're going to write as 3 factorial. And it'll be 1 minus z to the minus 4. And the value of the third derivative at 0 is simply going to be 3 factorial into 1 minus 0 to the minus 4, which is just equal to 3 factorial. So we can see a trend appearing here right now, and we can generalize these terms at this point. So we would have the nth derivative of z is simply equal to n factorial into 1 minus z. And now we have minus n in the exponent, but 1 less than minus n. So you can see that the third derivative here, we have minus 4. So we have to take minus n and subtract 1 from it. So if we find the nth derivative at 0, then we see that it's simply equal to n factorial into 1 minus 0 to the power minus n minus 1, and that just gives us n factorial. So we now substitute these terms into our series expansion. So if we do that, so we just bring this here now down. So we have f of z, and the first term is f of 0. f of 0 is 1. And the second term is z, so we write z. And f prime 0 is 1, so we have to multiply it by 1. And the third term, we have z squared. Then we have the second derivative, and that's equal to 2 factorial. So we have 2 factorial, and we're dividing by 2, or 2 factorial. And the third term we have z cubed. Then we have the third derivative, at z, with z is equal to 0, which we can see is 3 factorial. And we divide by 3 factorial. So it carries on in this manner, and then we have z to the power n, fn at 0, which we can see is n factorial. Put that in. And we divide by n factorial. So all of these factorial terms will cancel out. They become 1. So what are we left with? We are left with the fact that this series expansion is equal to 1 plus z squared plus z cubed plus then z to the power n, and so on. We need to understand whether this series is actually valid, where it's valid, for what values of z is it valid. So when we're asking about its validity, we're actually asking about its convergence. So we need to check in which ranges of z is it valid, because remember that if we look at our function, our original function, with which we had applied this series expansion for, which is this, we can see that we have a singular point where z is equal to 1. So what does this mean? How do we interpret that, and how do we go about checking in general for the ranges of values of z for which this kind of function is valid? So we're going to talk about that in the upcoming video, and we will talk specifically about the ratio test. Hi there. Thus far, we've been talking about the Maclaurin series expanded out for complex variables. The last time we had seen the general form of the Maclaurin series. We had seen that we have to take the function at the region of 0, we have to add to it z multiplied by the first derivative at 0, plus z squared times the second derivative divided by 2 factorial, and so on. And we had done this for a certain example. So the question at that point was, how do we know if this series expansion is valid for the function that we have considered? How do we know that this is something real that we are actually doing? So in other words, we need to establish if the series that we have written for some kind of function actually converges. So the way to do it is by using the ratio test. So in general, if we have some kind of function, and if we want to see if that function converges, so we can consider just this exponential function. It goes like that, and we can see that the x-axis is the asymptote. Okay, it's getting closer and closer to 0. We can see that as x gets bigger, this function gets smaller and smaller and smaller until it gets very close to 0. So in general, this is what we would like to see for a function that converges. If we were to write out some kind of expansion, like 1 plus 0.5 plus 0.25 plus 0.125, and carries on like that, eventually this is going to get smaller and smaller and smaller, and it will be on the order of 0.0001 and so on. So it's going to become something very small. So eventually it'll reach a point where we're just adding almost 0 to this series. So that means that this series has reached some kind of definitive value, or close to some definitive value. And the key characteristic of this is that the next term in the series is smaller than the last. You can see the third term is 0.25 and the second term is 0.5. So each next term is smaller than the one before it. So we can make use of that fact. That is the fact that we use when we are applying the ratio test. We can generalize this a bit more, and we can write a function x as being the sum of some polynomial. So a0 plus the second term is a1 as a function of x, plus a2 as a function of x, and so on. And then we would have an to the power of, as a function of x. So when we write the ratio test, we are applying the fact that the next term is smaller than the last. So what we're looking at is the next term. So the general term is an. Any one of these things could be an. So if we're considering the next term, we are saying an plus 1 as a function of x, and we divide that by the term before that, which is an. And if this next term, an plus 1, is actually smaller than the previous term, then it should actually be less than 1. We should actually have a fraction. We can see that if we take 0.25 and we divide it by 0.5, then we actually get 0.5. Let me just write that a bit better. If we take 0.25 and we divide it by 0.5, then we get 0.5, which is less than 1. So we are applying this logic here. So what we're doing is that we're taking the ratio of these terms, we're applying the absolute value, and we're taking the limit as n approaches infinity. When we do that, we would have computed some number, call that L, and when this L is actually less than 1, then we know that the series converges. So this is the key point here. We have to check using this ratio that L is less than 1. So if L is more than 1, then it means that the series diverges. So if L is equal to 1, then we have a situation where the ratio test doesn't actually work, and we have to use some other method to establish if the series converges. So let's just apply that logic to a simple example. We could have the function f of z is equal to sine z. So firstly, we're going to expand this in terms of the Maclaurin series, which we can actually see here on the top. So there's the Maclaurin series. So we have to compute f at 0, the derivatives, and so on, and we put this entire thing together like that. So firstly, we compute f at 0. So let's write it here. So we have f of 0, which is equal to sine of 0, which is just 0. Then we have the first derivative, which we need. Derivative of sine is cos. So we have cos z. Then we compute the first derivative at 0. So we have cos of 0, which is actually equal to 1. Then we compute the second derivative at z, and we see that that is minus sine. Derivative of cos is minus sine. We have minus sine z. Then we compute that second derivative at 0. So minus sine of 0 is just equal to 0 again. Then we compute the third derivative at z. The derivative of minus sine is minus cos. And then we compute the third derivative at 0. So that's minus cos z of 0, which is minus 1. Okay, so if you look at the pattern here, the derivatives are taking on the value of 0 for even numbers, and then we have alternating between 1 and minus 1. So let's write our series expansion, Maclaurin series, for this particular example. So f of z is equal to the first term is f of 0. We can see that that's 0, so we write 0 here. Then the second term is z, and then we have to multiply that by the first derivative, which is 1. And then the third term is z squared. Then we have to multiply that by the second derivative, which is actually 0. Then the third term is minus 1. We have z cubed times minus 1 divided by 3 factorial. And it goes on like that. So if we were to just simplify all of this, what would it look like? We would get f of z is equal to z, that's the first term here. We don't have even numbers, then we can see that the next term is a negative. So we have minus z cubed over 3 factorial. Then we have plus z to the power 5. Remember that even numbers are 0, being multiplied by 0, divided by 5 factorial. And we have minus z to the power 7 divided by 7 factorial, and so on. So if we wanted to have a general term for this kind of expression in terms of n, then what it would be is minus 1 to the power n multiplied by z to the power 2n plus 1. Okay, so that's 2n plus 1. So whenever we want to compute an odd number, then we would just say 2n plus 1. For example, if we take n is equal to 2, we'll get 2 times 2, which is 4. 4 plus 1 is 5. So that is z to the power 5. And then minus 1 to the power n. So n was equal to 2, so minus 1 to the power 2 is plus. We can see we have the plus here in front. And then we just have to divide by that 5 factorial. So the way we'll write it is, same way we want the odd number. So it's 2n plus 1 factorial. So now we are in a position to apply this ratio test. So there's the ratio test here, and that's what we're going to use. So this L was equal to the limit as n approaches 0, sorry, n approaches infinity, of firstly a n plus 1 divided by a n, and we take the absolute value. So if we were to write it now for this term, so we have a n, so this is what a n is equal to. So this is the term that we are dividing by. We're going to divide by this term, and the numerator is a n plus 1. So we're going to take the same thing, and wherever we see n, we're going to substitute it with n plus 1. So let's look at the numerator. So we have now minus 1, and then we have n plus 1, then we have z, then 2n plus 1, so that will be 2 into n plus 1, then plus 1, and then divided by, now this 2 into n plus 1 plus 1, so this plus 1 here is the one that we have to write here, and this whole thing is factorial. So that was only the numerator, okay? That was only the numerator. We now have to divide by this an. So that is minus 1 to the power n, z to the power 2n plus 1 divided by 2n plus 1 factorial. We now have to simplify this. We take the limit as n approaches infinity, and we write it out. Okay, we can simplify a lot of these things. So we have minus 1 to the power n plus 1. We have minus 1 to the power n plus 1. So we use our laws of exponents. This n is going to go to the numerator here, and we have to subtract it out. So we have 2 minus n. Then we have z to the power 2n. Then we have 2 times 1, which is 2. 2 plus 1 is 3. So we have 2n plus 3. And then here we have 2n plus 1 in the denominator. So we take that to the top, and we change the sign. So it's going to be minus 2n minus 1. And we take this entire term with the factorial to the top as well. So we have 2n plus 1 factorial. So now what's left? What's left is this term. So what it is 2n, then 2 times 1 is 2, then 2 plus 1 is 3. So we have 2n plus 3 factorial. Okay, but remember now what is factorial. For example, if we have 5 factorial, that is just 5 times 4 times 3 times 2. So we minus 1 each time. So that's what we're going to do here. So this 2n plus 3 is the same thing as writing 2n plus 3, then we minus 1. So we have 2n plus 2. Then we have 2n plus 1. And we can keep multiplying that out. So beyond this point here, so beyond that point, we can just simplify that whatever is going to come afterward as factorial at that point. Okay. What we have essentially said is, for example, 5 times 4 times 3 times 2, etc. So we can simply just say that this is 5 times 4 factorial. That's what we've essentially done. What that means is that this term cancels out with that. And also what we're left with here, we're left with minus 1 to the power 1, which is just meaningless because remember we're taking the absolute value here. And then we have 2n minus 2n cancel out, and then 3 minus 2 is 1. Sorry, 3 minus 1 is 2. So we have z squared, 3 minus 1, giving us the 2. And in the denominator, we have 2n plus 3 and 2n plus 2. And we're taking the limit of this as n approaches infinity. So what we're saying that in the denominator, we have a number that gets very large. If we divide something by something that's getting very large, then what it becomes is 0. So this limit gives us 0. And what we see that 0 is less than 1. So what was our criteria? Our criteria was that when we compute this ratio, we should get that it should be less than 1 for it to converge. And of course, we can see that 0 is less than 1. So it means that there's no limitation on what value of z that this can apply to. It means that this expansion that we've done is actually valid for all values of z. It will converge. So in a nutshell, when we are applying a series expansion to some kind of function, we compute this ratio and we check for values of z for which this ratio is less than 1, and that will tell us if this series converges and whether we're able to use it. So thank you very much for watching. In the next upcoming videos, we're going to talk about applying this to the radius of convergence. We're going to look at other functions, and then after that, we'll start applying it to the Taylor series, the Laurent series, and we're going to look at residues and also how to calculate zeros and poles. Thus far, we've been writing complex variables to be the sum of a series, specifically the Maclaurin series. And we saw that the Maclaurin series, written where z is near 0, is equal to f0 plus z f prime 0, z squared, second derivative divided by 2 factorial, and so on. And in the last video, what we had looked was if this series is actually valid. In other words, does it converge? And we had looked at the ratio test to establish that. And we had seen that it converges for certain values. So what we're going to do is just extend this a little bit more and talk about the radius of convergence, in which we see that there is a specific region in which this particular series will actually converge. So we can start off by a basic example that fz is equal to ln of 1 plus z. So we start off as we usually do. We compute the function where z is equal to 0. So we have ln of 1 plus 0, which is just ln of 1, which is 0. Then we compute the first derivative, and that will equal to 1 plus z to the power minus 1. That's what the derivative of log is. And then we compute that derivative at 0. So we have 1 plus 0 to the power minus 1, and that gives us 1. And then we compute the second derivative, and that will be minus 1 into 1 plus z to the power minus 2. That's 1 plus z to the power minus 2. And then we substitute in 0 there, which we have minus 1 plus 0 to the power minus 2, and it gives us minus 1. And then the third derivative, that will just be 2, or we can say 2 factorial at this point, into 1 plus z to the minus 3. And then we substitute the third derivative, 0. We get 2 factorial into 1 plus 0 to the minus 3, which is 2 factorial. So normally we would stop at this point, as we had done in the previous videos. However, there isn't a clear pattern emerging in terms of the derivatives for us to generalize this series just yet. So we would just compute the fourth derivative, and that we see is minus 3 times 2, which is minus 6. So it's minus 3 factorial, in essence, into 1 plus z to the minus 4. And then if we substitute in 0, then we get minus 3 factorial into 1 plus 0 to the power minus 4, which is just minus 3 factorial. So at this point, we are at a position in which we can try and generalize this series. So when we generalize this, we want the nth derivative of z. Firstly, we can see that every even number takes on a negative. Okay? When n is equal to 2, we have a negative number. When n is equal to 4, we have a negative number. So to get that, we would say minus 1 to the power n plus 1. So that makes every even number a negative number. For example, if we take n is equal to 3, we'd want a positive here. Okay? So we substitute 3. 3 plus 1 is 4. Minus 1 to the power 4 is plus 1, and we can see that there's a plus 1 in front. So the next thing we need to do is incorporate that factorial. So we can see it's n less 1. So that's n minus 1 factorial. And then 1 plus z to the power minus n. So if we substitute 0 inside there, then what we're going to get is 1 plus 0 to the power n. And then all we're left with is essentially minus 1 to the n plus 1 times n minus 1 factorial. So if we substitute this into our Maclaurin series, then what we get is f of z is equal to f of 0, which we know is 0. Then we have plus z, so you can put that in. And then we have f prime 0. F prime 0 is just 1, so that is just left as it is. Then we look at the next term. We have z squared, and then second derivative at 0. Second derivative of 0 is minus 1. So we have a minus here, and then we have the z squared. And what else? Nothing else. But don't forget, we have to put in the 2 factorial. Then the next term, we have z cubed. And we see that we have a positive number here, and it's 2 factorial. So we have plus now z cubed. And then we have 2 factorial. And then divided by 3 factorial. And this would cancel out. 2 factorial divided by 3 factorial is simply just 3. 2 factorial is 2 times 1, and 3 factorial is just 3 times 2 times 1. So that would cancel off, and that's how we just get the 3 there. Then the next thing is negative. In the same way, this factorial can also come out with that term. So it alternates between positive and negative. So the next term is going to be minus z to the power 5 divided by 5. So we can see the Maclaurin series is like this, and this becomes generalized to z to the power n multiplied by minus 1 to the power n plus 1 divided by n factorial. So that is the Maclaurin series for this particular term. Also, we should not forget that there is an n minus 1. But it can cancel out. Okay? So we can write n factorial as n multiplied by n minus 1 factorial. And that n minus 1 factorial cancels out with that n minus 1 factorial. And then all we're left with is just n. So what we're going to do now is write the ratio test for this particular example. So the ratio test said that we compute some quantity L, and that is equal to the limit as n approaches infinity of the absolute value of an plus 1, which is some function of z, divided by an as a function of z. So the next term divided by the previous term. So we had seen how this is the case, and you can go back and revise the videos on this. So if we do that, we're going to have z, then we substitute n plus 1 everywhere. We have n plus 1, then we have minus 1 to the power n, then plus 1, and then plus 1 again. And now this is divided by, okay, also let's not forget the n. So we have n here, that's the n there. And this is divided by z to the power n, then minus 1, n plus 1, divided by n. Okay, that should be n plus 1 there. And of course, we are taking the limit of this as n approaches infinity. So when we compute this, we have z n plus 1, then we have minus n using the rules of exponents, and we have minus 1 to the n plus 2, and then we bring that to the top. We have minus n minus 1, and then we have times n. So this n will go to the numerator of the top term, and then this is all divided by n plus 1. And we are taking the limit here. So what we're left with is z. So this minus 1 will become minus 1 to the power 1, and we're computing the absolute value, so it doesn't really matter. So we have z times n divided by n plus 1, and we are taking the limit of that. So when we take the limit of this, we find that it is equal to z, okay? So the limit of this quantity becomes z. So what does this mean now? We haven't computed a specific number here. We haven't said that, remember that this quantity L is supposed to be less than 1, but we just have z. So what do we do here now? It means that this series will be only valid when z is less than 1. So what does that mean? Remember that this z is a complex variable. It is actually x plus jy, okay? So if you write it in the exponential form, that is r e to the power j theta, okay, this is actually z less than 1. We're saying that 1 e to the power j theta is actually less than 1. So we're talking now about a unit circle of radius 1. And if we were to draw that, okay, so this is supposed to be a unit circle of radius 1. So that's 1, minus 1, minus 1, and 1. So we're saying that this series will converge only within this particular radius. So this is called the radius of convergence. It is the specific region within which z will actually be less than 1, and this is where the series will actually converge. So that is the radius of convergence and the circle of convergence. However, there is one slight issue here. If we recall our original function, we had written the series expansion for the function ln of 1 plus z. So if we consider minus 1, where it's minus 1, z is equal to minus 1, then we see that this is not an analytic term, okay? It's not analytic at that point where z is minus 1. So in that particular region, it doesn't actually apply. So we're limited by the Maclaurin series because it has to be centered at the circle, at the center, sorry. So the circle of convergence has to be centered at 0, 0, the origin, because the Maclaurin series is applied specifically near the origin. So what we actually want to do is to be able to draw the circle of convergence at any point in the plane, okay, in the z-plane, centered at any point in the z-plane. So how do we go about it? We have to shift it in some way. So that is done using the Taylor series. In this video, we're going to talk about the Taylor series expansion of a complex variable. Thus far, we've been speaking about the Maclaurin series, and the Maclaurin series expansion is applicable for where this complex variable z is equal to 0, or it's rather in the region where z is equal to 0. And we had seen that the expansion took the form where the first term was just the function where z is equal to 0. The second term was the variable z times the first derivative at 0. Next term, z squared times second derivative at 0 divided by 2, and so on. So there are some limitations of expressing the function to be in terms of the Maclaurin series. And the first one is, of course, well, it's only near one specific point, which is the point of origin. And also, when we consider the region in which the series expansion is valid, then we see that we actually limit it to the radius of convergence just being centered at the origin. In other words, the region in which the function is actually valid for in the z-plane is a circle of convergence as we had called it, and it's centered at the origin. So we want to consider now where a circle of convergence is not actually centered at the origin. So in other words, we could have our z-plane and our circle of convergence is here, for example. So in that instance, the center now takes on the value z0. So this is z0. So how now do we move from this circle being centered at the origin to this circle now being centered at z0? We have to move it along. So the key here lies in the fact that we have considered the Maclaurin series to be at nearby z is equal to 0. So what we're going to do is we're going to move it from 0 to this new value z0. So that is z0. So what we're going to do is we're going to write the series just as it is in the same form, because the Maclaurin series is just a specific case of the Taylor series, and all we're going to do is substitute this 0 for z0. So we have fz is equal to the first term. We'll just replace that. So we have f at z0, and then now we have z. Okay, what we do here is we replace this z with z minus z0, and that remains the same, the first derivative. So we have f prime, but instead of 0 we have z0, and the rest of the expansion follows that same pattern, where we replace z with z minus z0 squared, second derivative at z0 divided by 2, and so on. So this is actually the Taylor series. So that is a more general form of what we have actually shown. So this new circle of convergence that we have just drawn, that could have a radius r, for example, whereas, okay, this may be a unit circle that on the left here that we have. Circle of convergence could be represented as z being equal to 1, where the z is the size of it. Here we would write it as z minus z0 is equal to some radius here, r. We could also write this as z minus z0 is equal to r e to the power j theta. So that would be the polar form. So the easiest way to illustrate how to write the Taylor series for a certain function would be to do it with a simple example. The example that we'll consider is f of z is equal to 1 over z plus 1. So how are we going to do this? Well, we have to write this series expansion for this function about a certain point z0, okay? So in this example, we'll write this function about the point where z is equal to 1. So we want a Taylor series expansion of this function near z is equal to 1. So how do we do this? The easiest way to do this is actually to perform a transformation. So what we're going to do is we're going to create a new variable u, okay? So this new variable u will be a function of z, and what we'll say is u is equal to z minus 1. Why have we chosen this particular transformation? The answer to that question lies in the fact that we are writing the series about z is equal to 1. So if we were to substitute z is equal to 1 here, we'll have u is equal to 1 minus 1, which is equal to 0. What's the significance of this? The significance of this is that now we have transformed this point to be 0. And that tells us for this new variable, writing the Taylor series here in terms of z is actually the same as writing the Maclaurin series for this new transformed variable. What does the Maclaurin series say? It says that it's just a specific case of the Taylor series where z is equal to 0. So that's what we can do. We have now created a new variable where everything is now near 0 for that new variable. So now let's transform this function to be in terms of u, and then write the Maclaurin series for that function, and then we transform it back, and then we have the Taylor series about z. So let's illustrate that. So now we will write this in terms of u, and this is 1 over z minus 1. So u is equal to z minus 1. So what that means is that z is equal to u plus 1. Okay, I've just taken minus 1 to the other side. I've written this in terms of z. So I substitute that in. So I have z plus 1 here. So I'm going to replace that z with u plus 1. Okay, then plus 1. So that gives me u plus 2. And now I write the Maclaurin series for that. And when I do that, I'll just play around with these terms a little bit. So f of u is equal to 1 over u plus 2, and that is also the same as writing it as 1 over, I take out 2 as a common factor, 2 into 1 plus u over 2. So that's u over 2. I've written that as a common factor. So this is the same thing as a half into 1 plus u over 2 to the power minus 1. So I write now the Maclaurin series for this expansion, for this function. So the first thing I need to determine is where this function is equal to 0. So I have a half into 1 plus u over 2 to the power minus 1, and u is 0. So I put in 0. So what I'm left with is a half. So now I find the derivative here. So that is simply equal to minus 1 over 4. So I have minus 1 times a half is minus a half. And then the derivative of the inside function is a half. So I have a half times a half. That gives me 1 over 4 into 1 plus u over 2 to the power minus 2. Now I have f prime at 0, and that's equal to minus 1 over 4 into 1 plus 0 again, and that is equal to minus 1 over 4. This should also be to the power minus 2 there. Then the second derivative, that's equal to minus 2 times 1 over 4. That's minus a half, or rather minus times minus gives us a plus. So I have half, then half times this inside function derivative is also a half. So that gives me 1 over 4 again. So I have 1 over 4 into 1 plus u over 2 to the power minus 3. The second derivative, there is going to be 1 over 4 into 1 plus, again, 0, which is 1 over 4. So I do it one more time for the third derivative. If I have minus 3 times 1 over 4, that's minus 3 over 4. Minus 3 over 4 times a half is minus 3 over 8 into 1 plus u over 2 to the power minus 4. I substitute in 0, and I have minus 3 over 8 into 1 plus 0 to the minus 4, which is equal to minus 3 over 8. So I can substitute all of these terms in the Maclaurin series. So let's just remind ourselves what that is. So I have f of u in this case here. That's equal to f of 0 plus u times f prime 0 plus u squared times f prime 0 divided by 2 plus u cubed times the third derivative at 0 divided by 3 factorial, and so on. So I substitute these terms in. F at 0 is a half, so that's my first term there. Half plus f prime 0, which is minus 1 over 4. So I have minus here. Minus 1 over 4 times u. And then I have u squared, and then I have 1 over 4. So now I have 1 over 4, that's f second derivative here, divided by 2. So this one is actually 1 over 4 times 1 over 2, which is 1 over 8. So I have 1 over 8 u squared, and then I have 3 over 8 divided by 3 factorial, which is 3 times 2, which is 6. So 3 over 6 is actually a half. So I have a half times 1 over 8, which is actually 1 over 16. And then there's a minus there, so it's minus 1 over 16 times u cubed, and so on. So this is the Maclaurin series in terms of u. However, we wanted the Taylor series for z. So what's the relationship between u and z? It's simple. U is just equal to z minus 1, or z is just equal to u plus 1. So all we just do is make this substitution. Wherever we see u, we just put in z minus 1. So what this means is that the Taylor series for z is that we have a half minus 1 over 4 into z minus 1. Remember that this is what u is equal to. U is equal to z minus 1. There's it here. That is the transformation that we applied. Then the next term is plus 1 over 8 into z minus 1 squared minus 1 over 16 into z minus 1 cubed. So if we wanted to generalize this expression, then what we would write is, okay, we have half, quarter, 1 over 8, this is 1 over 16, and so on. So we have z minus 1 to the power n. That's evident. There's 1, 2, 3, it's to the power n. And then this 2, 4, 8, 16. So these are just powers of n. Specifically, it's 2 to the power n plus 1. So that is the Taylor series for this complex variable here. If we wanted to find the circle of convergence, all we would do is we would take this general term, and apply the ratio test. We would say where n approaches infinity of this term here plus 1, n plus 1. Remember that it's a n plus 1 divided by a n. This is according to the previous videos we had done. And if we apply it to this example, we have the limit as n approaches infinity. And we substitute n plus 1 here. So we'll have z minus 1 to the power n plus 1. We just substitute n plus 1 instead of n. And then we divide it here by 2 to the power n plus 1 plus 1. So it's n plus 2. And now we divide this by what we see here. So it's z minus 1 to the power n divided by 2 to the power n plus 1. So this is equal to the limit as n approaches infinity of, firstly we'll have z minus 1, then we have n plus 1, and then we take this n to the top, it becomes minus n, and then we're dividing it by 2 to the power n plus 2, and then we minus n minus 1, and then what we're left with is the limit as n approaches infinity of z minus 1. Okay, that's what we have there, divided by 2, just 2, right? 2 minus 1 is 1, and n minus n is 0. So this is just, there's no n here, so there's nothing to take to infinity. So this is just z minus 1 divided by 2. And we know for a fact that this actually has to be less than 1. Okay, this has to be less than 1 for this ratio test to apply, for the series expansion to be valid. Okay, so what this means is that z minus 1, okay, actually needs to be less than 2. And we can see that this is a circle. So it's actually the circle oriented near where z is equal to 1 and having the radius of convergence to be of size 2. So that is the interpretation there. So this video actually showed now how to extend the Maclaurin series to write the Taylor series about any point. And to do this, all we do is just a simple transformation. We transform our function to be a new variable and then just write the Maclaurin series for that new function and then convert it back to be in terms of the Taylor series, and that gives us our Taylor series for that function about a given point. So thank you very much. In this video, we're going to talk about poles, essential singularities, and removable singularities. So previously we spoke about analytic functions, and we said the characteristic of analytic or regular functions is that they are defined, single valued, and that the derivative exists. However, there are points in which these criteria are not met. And if we were to consider a simple illustration of this, we could consider the function f of z is equal to 1 over z minus 1. So if we analyze this, we see that it is not analytic. So it is not analytic at z is equal to 1. If we substitute 1 inside this function, we see that 1 minus 1 is 0. We have 1 over 0, which is obviously not defined. So we say that at z is equal to 1, there is what's called a singularity or a singular point. So the question in this video is, how do we interpret the singularity? Is there different kinds of singularities, and how do we go about just understanding this whole thing? So the way this whole thing is sort of characterized is by looking at how does the function go to infinity. If we said that we have 1 over 0, it means that this function goes to infinity. In other words, it becomes very large. So how does it approach infinity? Does it approach infinity in a controlled way, or does it approach infinity in an uncontrolled way? And the way that happens actually affects this criteria or this characterization of singularities. So the first type is a pole. So when we speak about a pole, what we're actually saying is that this function approaches infinity in a controlled manner. So when I say controlled manner, I will just give an illustration of what I mean. So we have poles. So the easiest way to illustrate this would be through an example. So we have a function, and that's f of z is equal to 2z over z plus 4 squared. So the question is now, what are the poles? So firstly, we see that there is a singular point at minus 2. So at z is equal to minus 2, we have our singularity. So the way we check if this singular value approaches infinity in a controlled way is by considering a certain limit. So maybe I should just mention here that the key characteristic about poles is that infinity is approached in a controlled way. Controlled way. So what we do is, firstly, we take this function f of z, so that's 2z into z plus 4 squared. Okay. What we do is we multiply it by this denominator, that's z plus 4 squared. Okay. So this is the technique. And then what we do is, for this expression that we have just written, we take the limit as z approaches this singular value, which is minus 4, sorry. Shouldn't have been minus 2, it's minus 4. So we can see clearly here that what we are doing is we are kind of cancelling out this singular value, right? So this part of the expression that makes it into a singularity, we are sort of removing it out. So we are sort of cancelling out singularity. So the reason why we do this is because this limit gives us a way to see how this function actually approaches infinity. We can see that we cancel out this term, and what we're left with is the limit as z approaches minus 4 of 2z. And we can see that this is minus 8. So when we get a value that is not equal to 0, okay, when we get a value that's not equal to 0, it means that it's actually a pole. We can call it the term a pole. So a pole is a singular value in which approaches infinity in a controlled manner, right? So this limit gives us this non-zero value, and because it's non-zero, it tells us that as we approach the singular point, this function goes towards infinity in a controlled manner. This is the thing about poles. So to find a pole, all we do is we compute this limit, and we can write this limit in a general way. So that limit written generally is that it's the limit as z approaches some kind of singular value, that's z0. In this example, there is -4. And we write this limit generally as z minus z0 multiplied by the function of z. And also we have to raise it to the power n. So this to the power n tells us the strength of how it approaches infinity, the function that is. So this is what a pole is. So just to summarize once more, we have a function, we have its singularity, and it's a pole if this function, this limit that we've just computed now, is not equal to 0. On the other hand, we can have a function, for example, f of z is equal to e to the power 1 over z. Now we can clearly see here that we have a singularity where z is equal to 0. Okay? So in this case here, we can't sort of directly and clearly cancel out this pole from this, sorry, not this pole, but the singularity from this expression. But what we can actually do is just take the limit as z approaches 0 of this function itself, which is e to the power 1 over z. So what do we see happening here? So let's just take two values. Let's just say, for instance, that, z is equal to 0.1, right? So what this means is that we're going to have e to the power 1 over 0.1, which is e to the power 10. Now, e to the power 10 is a huge value, okay? It's a very big number. On the other hand, if we take z is equal to minus 0.1, then what's actually happening is that we're going to have e to the power minus 1 over 0.1. Okay, so this is supposed to be 1 over 0.1. Then what this means is that we have e to the power minus 10, and this is very small. So as we approach 0, okay, this function fluctuates between extremes. So what we're saying is that it doesn't approach infinity in a very controlled manner, right? So whereas with a pole, we computed this limit, and we can see that, okay, there's a very clear, distinct way in which this function is going to approach infinity in a very linear manner. On the other hand, we have this function here, and we see that, okay, we have wild fluctuations in the values as it approaches 0. So this function is going to fluctuate wildly as we approach the singularity. So in this case here, what it's called is an essential singularity. So an essential singularity is just a point in which the function approaches infinity in a very uncontrolled way as z approaches this singularity. The last type of singularity that we're going to talk about is that of a removable singularity. So it is a removable singularity. An illustration of this would be the function fz is equal to sine z over z. Okay? If we first just look at this, we can see that we have a singularity at, again, z is equal to 0. However, we can't actually classify this as a pole or a essential singularity. And the reason for this is because this function, where z is equal to 0, actually exists. There is actually some kind of convergence. In fact, the function converges to 1. So in other words, if we take the limit as z approaches 0 of this function, that's sine z over z, then this actually converges to 1. We can see this by expanding the Maclaurin series. So if we were to expand the Maclaurin series of sine z over z, okay, and we take the limit of that, so the Maclaurin series of sine z over z is 1 minus z squared over 3 factorial plus z to the power 4 divided by 5 factorial, and so on, and so on. I've shown in previous videos how to actually determine this type of series. But anyway, if we exclude the terms where z is going to go to 0, which is every other term besides the first term, then we see that this is equal to 1. So what that tells us is that it's not actually a singularity like how it is with a pole or a essential singularity where the function is not actually defined, it goes to infinity. In this case here, it's more that the function has a kind of missing value, so to speak. So to put it very loosely. So we just put in that missing value just by considering the limit as it approaches that singularity. So in this video, we've just discussed 3 types of singularities. The first one is a pole. We just see that the pole is simply a singularity where the function approaches infinity when z approaches the singular point in a controlled manner. Okay? An essential singularity is essentially where the function fluctuates wildly as z approaches the singularity. And then lastly, we have a removable singularity where the function just has a sort of missing value at the singularity. So these are the 3 most common kinds of singularities that are analyzed in complex analysis. In this video, we're going to talk about the Laurent series and residues. In the previous videos on complex analysis, we've considered the Maclaurin series and the Taylor series as expansions of different complex variables. We saw that the Maclaurin series has this particular form, and the radius of convergence is actually centered at the origin. So that is the radius of convergence of the Maclaurin series. We saw that a limitation of this is that we can have a singularity on the boundary of the circle and perhaps even within the circle of convergence. So how we dealt with this issue was considering the generalized form of the Maclaurin series, which is the Taylor series. With the Taylor series, we can move this circle of convergence to, instead of being centered at the origin, to be centered at some other arbitrary point, maybe z0. So in this way here, we have now considered some kind of series expansion outside of our singularity. And of course, the only difference in the actual expansions is that where we would have 0 in the Maclaurin series, we substitute that with our arbitrary point, that's z minus z0. Now we consider a situation in which we no longer just want to consider the series expansion around a point, okay? We want to consider the series expansion specifically around the singularity. So that's what we want to do. We now want to expand some kind of series, a polynomial series, around our singularity itself. So in the Taylor series, it doesn't really help us because we had used it to move the circle of convergence away from the singularity. So then what do we do? Well, what we're going to do is to start by considering what we're actually doing. So we have our z-plane, and we have our singularity, and it's at some point z0. So we have 2 curves. This curve, we call that the outer curve. Maybe we'll call that C1. Just around the singularity itself, we have another curve. So we'll call that maybe C2. Okay, I'll just draw it a bit bigger. So that inner curve is C2. So our region that we're considering in this particular scenario is actually between these curves C1 and C2. So it's actually this region inside. So this is an annular region. And when we are considering a contour or some curve or something like that, it's actually falling in between these 2 curves. So in between C1 and C2, we have some generic curve C, which we'll be applying this analysis to. So just to repeat it once more, Z0, that is our singularity. And we are analyzing this system in which we are now going to write the series expansion about C. So C is the closed curve. And we'll also need to say that f of z, some function, is analytic. So it's analytic in this annular region. So this region that's highlighted in red is analytic. Analytic in annular region. So how does the Laurent series actually look? What form does it actually take? Well, it's actually very similar to the Taylor series that we've seen thus far. There are some differences, but let's just write the generic form of it. So we have our function fz. In this Laurent series, we're going to have a term a0 that would be associated with some subscript n being 0. Then we would have a1, that's another coefficient with n equal to 1. And we would have z minus z0, and we would have plus a2 into z minus z0 squared, and it would carry on in this manner. However, the series expansion doesn't start with n equal to 0, whereas the Taylor series and Maclaurin series would start with n equal to 0. This one actually starts from minus infinity. So we have terms to the left of this a0. So what are the terms to the left? Well, it just carries on in that same manner. We have z minus z0 now to the power minus 1. And the coefficient in front of that term is a minus 1. So here's a is equal to 0 and here a is equal to minus 1. And it will carry on in this manner. So it goes on from infinity. Maybe we could write another term. We'll have a minus 2. Then we have z minus z0 to the power minus 2. And it carries on like that. So if we were to write a generic form of this Laurent series, what it would actually look like is f of z is equal to the sum where n goes from minus infinity to infinity of a n, okay, these coefficients, into z minus z0 to the power n. So this series can be easily evaluated if we know these coefficients a0, a1, a2, a minus 1, a minus 2, and so on. So we can derive some general expression for an, and we can do that now. We can just compare it firstly to the Taylor series. Here's our term z minus z0. So if we go back up to the Taylor series, there's our term z minus z0 squared. So whereas the coefficient was this second derivative at z0 divided by 2 factorial, it's just essentially been lumped into one coefficient. So as I was saying, what we're going to do is derive an expression for this an, and some interesting results come out of this whole thing. So the first thing I'm going to do is replace this index. I'm going to replace n with m. So we're going to have fz is equal to this sum, where now m starts from minus infinity and goes to infinity. And we're going to have am into z minus z0 to the power m. So why have I done this? Well, I'll need to compare m and n at some point. They are the same, they are equal, but I have to state that in a specific way to get a certain result. So the first thing that we're going to do in this derivation is that we're going to divide both sides of this equation by z minus z0 to the power n plus 1. Okay? And we divide the right-hand side. So we have z minus z0 to the power n plus 1. So I just simplify this right-hand side. So I'll get f of z divided by z minus z0 to the power n plus 1. And then that will equal to, this sum remains the same. We're going from m minus infinity to infinity, and this coefficient am. And then we can just simplify this. We have z minus z0. We have this m. We take this n plus 1 to the top. It becomes minus n minus 1. So what I'm going to do now is I am going to multiply both sides by the differential dz. Then I am going to integrate both sides. Around this closed curve C. I do that for the left-hand side, and now I do it for the right-hand side. I integrate around the closed curve C. And let's just remind ourselves what that closed curve C is. C is that orange line in this annular region. So now that I've done that, I can proceed with this derivation. And the first thing that we must realize is that since it's happening within the analytic region, this is actually going to converge, okay? So this sum is going to converge. And since this integral and the sum, well, it's converging in that around that contour, we can actually swap them around. So that's what we're going to do. We're going to swap around this integral and the sum. So we're going to write integral here around this closed curve, and then the sum as m goes from minus infinity to infinity. So now that I've done this, I need to evaluate this integral on the right-hand side. So this integral now that I've indicated in the square brackets, I want to evaluate that. So I'm going to bring that out. So I have integral now around this closed curve of c of a m into z minus z naught to the power m minus n minus 1 dz. So this is an result that, or the result of this integral is something very important in complex analysis, okay? We have to consider two scenarios. The first scenario is where this index m minus n minus 1 is equal to minus 1. So this integral, this index m minus n minus 1, this exponent, sorry, where this exponent is equal to minus 1. So when this exponent is equal to minus 1, what we're actually saying is that m is equal to n. Okay, this is very obvious to see. So we're now going to evaluate this integral for this particular scenario. We can take this am out of this integral. We can put that as part of the sum. So what we're evaluating now is the integral around this closed curve of z minus z naught to the power minus 1, okay? As I said before, or just now, was this exponent takes on the value minus 1. So we are evaluating this integral where this exponent is minus 1. So how do we go about doing this? You might ask at this point, okay, isn't the integral around a closed path of some kind of complex variable, isn't it just 0, right? Isn't it just 0? Well, it's only 0 if that region is analytic. Remember the Cauchy-Goursat Theorem we had looked at in the previous video? So that only applies if we are considering the entire region being analytic. In this case here, we have a singular point. So we're considering now where we have a curve and we have a singular point singularity inside it. So in that instance, the Cauchy-Goursat Theorem does not apply. Okay, so this integral does have a value. So how do we evaluate this integral? So what we're going to do is we're going to let this z minus z naught equal u. So we let u equal z minus z naught. We have done a substitution. So if u is equal to this, then it means that du is equal to dz. And also, since this is a complex variable, we can also say that u is equal to r e to the power j theta, okay? This is the polar form of a complex variable. So this is what we're going to use to evaluate this integral. So this integral now, around this closed path of z minus z naught to the power minus 1 dz. So that's just equal to this integral around this closed path of c of u to the minus 1, okay, u to the minus 1. We will write that as 1 over u now times du. So if du is equal to dz, then du is also equal to this derivative of this r e to the j theta. And if we take this derivative, then what we get is the exponent of e to the power j theta is just e to the power j theta. Remember, our changing variable here is theta. R is just a constant and j is the square root of minus 1. That doesn't change. So if we're taking the derivative of du, then theta is our variable. So j theta is our inside function. So what that means is that the derivative of the inside function is just j. So we're going to have j times r, okay? Just to repeat that once more, derivative of du is equal to r e to the j theta. Derivative of e to the power j theta is e to the power j theta. And the derivative of the inside function is just j. So we multiply it by the outside using the chain rule. So now we substitute all of these things in. We have the integral around this closed path of c of 1 over u. So we have 1 over r e to the power j theta. And now we multiply this by du. and du is jr e to the power j theta d theta. So we write that out. We have r e to the power j theta times d theta. So what do we see? This e to the power j theta, e to the power j theta cancel off. Sorry, there's a j here as well. I just need to write that. I'll just write that there. Okay. And this r cancel off. Okay. So all I'm left with is just j. I have integral of j d theta, and now integral around a closed curve. So we have a closed curve and we have theta. So what is the integration bounds of a closed curve? The closed curve is just 0 to 2 pi. Remember that there's 2 pi radians in the circle. So one complete circle is just from 0 to 2 pi. So we have j d theta. There's j here and there's d theta there. So this integral you can easily see is just j times 2 pi. So that's what this integral is. So we can write that as an important result. That important result is that this integral around the closed curve of z minus z naught to the power minus 1 dz, this thing here is simply equal to j times 2 pi. So that was the one scenario where this exponent inside this expression was minus 1. So what about everything else? What about when its exponent is everything else besides minus 1? So we have this integral now. We have this integral of z to minus z naught of m minus n minus 1. And now we have to consider the scenario where m minus n minus 1 is not equal to minus 1. Okay, so this is the scenario where m and n are not equal. So when m and n are not equal, all that happens now is that this entire integral becomes 0. This whole integral becomes 0. So that is an important result. This is another major important result. How would we prove that? We would prove it in the exact same way that we had done this year. Okay, so I'm not going to do the full proof. It's a simple thing to do. It follows the same procedure. So we let u equal to z minus z naught. And now, if we're saying that m minus n minus 1 is not minus 1, then we have this integral now around this closed curve of u of, u to some index, okay, to some index. We'll call that k. And maybe this would be m minus n minus 1, okay? So it would be u to the power k. And now we would do the exact same thing. We would now need to do this r. So instead of now u equal to r e to the power j theta, as it is here, right? We would now need to have u to the power k, okay? And now we'd raise all of this now to the power k, and we would carry on in this fashion. But the moral of the story is that all of this becomes 0. So you can proceed with that proof or look it up in a textbook or something like that. So in any case, this thing is equal to 0. So now we have our expression for this coefficients of this Laurent series. This is where we are. We are here. We are here. We wanted an expression for this coefficient. Okay, so let's just proceed from that point so that we don't lose track of where we were. So the last thing that we had written was that we have this integrals that we are evaluating. We have this integral around this closed curve, this left-hand side, and that was fz dz divided by z minus z naught to the power n plus 1. This is now equal to our integral around this closed curve. Sorry, we had interchanged the sum and this integral. So we have sum where we have m and n, and now we see from our results here that since we are only considering the scenario where m is equal to n, which gives us this value j2 pi, this is all that we are considering, right? We are only considering the scenario where m and n is equal, because everywhere else where m and n are not equal, this integral gives us 0. So there's no point in considering it. So we are only considering where m is equal to n, and that's why we have now replaced this m with n. and n is going from minus infinity to infinity of an. Now this integral around this closed path of z minus z naught, okay, m minus n minus 1 dz, okay, and we saw that this entire thing is the same, so we just replace this with minus 1. M minus n is the same, so this becomes minus 1, and we saw that now this entire thing, so let's write the left hand side first. We have fz dz. Now we're dividing that by z minus z naught to the power n plus 1. This is equal to, firstly, okay, we saw that this integral is 0 everywhere else besides where m is equal to n, and it just takes on that value n. So this sum doesn't have any meaning because this integral is only going to give us one specific value. It's going to give us j2 pi only where we consider the value n. So we're going to replace all of this with an, okay, that's the coefficient here, and the sum of this, remember that this means sum of the integral. So we compute the integral for different values, okay, and we would take the sum of it. But it doesn't make any sense here at all because there's only one value that is valid, and that is for n, and it takes on that value j2 pi. So we would have an then multiplied by this integral, which is j2 pi. Just write the j in front, and we have times 2 pi. So all we do is we solve for an, and when we solve for an, then what we get is that this thing is equal to 1 over j times 2 pi times this integral around this closed path of f of z times dz divided by z minus z naught to the power n plus 1, okay? We can just remind ourselves what we're doing. We're doing the Laurent series, and the Laurent series f of z is equal to expression from minus infinity to infinity of a minus 2 z minus z naught to the power minus 2, then we carry on a to the minus 1 z minus z naught to the power minus 1 plus a naught plus a1 z minus z naught to the power 1, and so on, okay? So all of this coefficients can be evaluated using this expression that we have derived, okay? We can write it like this. So what we're going to do now is something interesting, okay? We are now going to integrate fz. We're going to take the integral of fz around that same closed path. So we're going to integrate fz dz around that closed path of C. And we're doing this with fz, so we can do this with each term of the Laurent series. And if we do that, we have the integral around this closed path of a to the minus 2 into z minus z naught to the power minus 2 dz plus a minus 1, integral around the closed path of a minus 1 into z minus z naught to the power minus 1. There should be a dz here as well, plus this integral around this closed path of a naught times dz plus integral around the closed path of a1 z minus z naught to the power 1, and we carry on like that, okay? So does it make sense to do all of these integrals? Does it make sense to evaluate all of them? No. If we do that, we will be wasting our time. Why will we be wasting our time? We will be wasting our time because we saw just now that when we evaluate this specific integral, z minus z naught, to some indice, it only has a value when this exponent is minus 1. So if I just scroll up a little bit here, we saw in this derivation that we have a value for this integral, okay, this integral, only when this exponent is minus 1, and it's that value j2 pi. Everywhere else, for every other exponent, this integral is equal to 0. So What this means is that the integral around this closed path of fz dz is equal to 0. It's 0 for all terms except where this exponent is minus 1. Z minus z naught to the power minus 1 dz plus 0, and everything else is 0. Okay? And what's the value of this integral? This value of this integral is simply j2 pi, which we had derived earlier. So this thing is just j times a to the minus 1 times 2 pi. Sorry, not to the minus 1. It's a of minus 1. So this a minus 1, that is given a particular name. So the name that it is given is a residue. It's called a residue because residue means what's left. So when you integrate the series expressed as the Laurent series, all you get is this term here with this coefficient a minus 1. So it's what's left when you integrate this function expressed as the Laurent series. So this is what the residue is. In this video, we're going to talk about how to calculate residues. We had seen in the last video something called the Laurent series, and the Laurent series was written as is on the screen right now, where we had some terms in which the exponents were negative and positive. And this was specifically for the region in which we wrote our circle of convergence with a singular point inside the circle. So then we looked at what happens when we integrate this function around a contour written in the form of the Laurent series. We then see we integrate each term of the Laurent series, and when we do that, we find an interesting result, which we had seen in the last video, that all of these terms go to 0 except for the term with the minus 1 as the exponent. Okay, so all of these terms go to 0 except for the one with the minus 1 exponent. So this integral just becomes 0 plus 0, then plus this integral with the minus 1, which takes on the value of j times 2 pi times this coefficient a minus 1 and plus 0. Okay, so the integral of this function only takes on the value for this particular term, which is this, and the residue was this coefficient a minus 1. So this has lots of applications in the sense where we can evaluate a very difficult integral in which we have a singular point within this circle of convergence, and it merely takes on the value of this integral if we can find this coefficient a minus 1. So we're just going to illustrate that with a simple example in which we have this radius of convergence, and we want to find this coefficient a minus 1, or we want to find the residue. So the function that we are considering is fz is equal to z over z plus 2 times z plus 4. So we are integrating this function along this contour, and it's a circle of radius 3. Now, the question here is, how does residues help us? Okay, firstly, to even write the Laurent series, this circle of convergence must be present in an annular region. So there must be an annulus between these this contour, right? So we could say, for instance, that this annulus, this contour could be between the annulus, where z is between 2 and 4. Okay, so if we were to draw z being more than 2, the circle z is more than 2, then it probably might look like this. Okay, and then z less than 4, maybe that might be outside here. Well, it is outside here, like that. So we can see now that our contour is inside this annular region. So that's good. That is what we want. So we can now expand this function in terms of the Laurent series. So the first step that we're going to do is we're going to take this function and split it up to be in partial fractions. So we'll say that z over z plus 2 times z plus 4 is equal to 2 over z plus 4 minus 1 over z plus 2. So that's what we get when we split up this function to be in terms of partial fractions. So now, if z is more than 2, which is this first part of this inequality, so if z is more than 2, and we have our term here, which is 1 over z plus 2, what I'm going to do is I'm just going to rearrange the denominator a bit, in which I will take out z as a common factor. So if I take out z as a common factor, then I get z into 1 plus 2 over z. Well, how does it help me? It helps me because I can write this expression 1 over 1 plus 2 over z in terms of the binomial theorem. Okay, so let's just bring that down. I have 1 over z into 1 plus 2 over z. So just a reminder of the binomial theorem. Okay, so the reminder of the binomial theorem, we have 1 over 1 plus x. So that's the same as 1 minus x plus x squared minus x cubed plus x to the 4, and so on. It carries on like that. So that's all I'm going to do. I'm going to write 1 over 1 plus 2 over z in this same form, but instead of x, I will have 2 over z. So this 1 over z, I keep the same. So then I write this as I've indicated here in this expansion. So I have 1, that's the first term, then I have minus, then 2 over z, then I have plus, then 2 over z squared, so that gives me 4 over z squared, and then the next term is going to be minus, then I'll have then 2 cubed, which is 8 over z cubed, and I can write it for each of the terms thereafter. So I can just expand this out, or I can multiply each term by z. So if I do that, then what I get is 1 over z minus 2 over z squared plus 4 over z cubed minus 8 over z to the power 4. And it will carry on like that. So I've done this for this expression. Now I can do it for the other term, that's 2 over z plus 4. So if z is less than 4, which is what we had said in this circle, there's our contour, there's the values of z, and we said that z is less than this red circle 4. So since that is the case, we can now take that expression 2 over z plus 4, and we can take out 4 as the common factor in the denominator. So I have 2 over 4 into 1 plus z over 4. 4 times 4 is 4, and 4 times z over 4 is z. So this 2 over 4, that is just 1 over 2. So I can write that as 1 over 2. So I can take this and expand it in the binomial series, binomial expansion, as I done with the first expression. So I have 1 over 2 into 1 plus z over 4. And if I expand that out, I get a half. And let's just remind ourselves, I think I erased it, but never mind, I can write it again. 1 plus 1 over x, that's just equal to 1 minus x plus x squared minus x cubed, and so on. So the first term is 1, then we have minus x, so it's z over 4. Then the next term is going to be x squared or z over 4 squared. So I'm going to have z squared over 16. Then the next term is going to be cubed. So I'm going to have z cubed over 4 cubed. So 4 cubed is 64. And it would carry on like that. So I just multiply this out. If I multiply that out, I get a half. And a half times z over 4 gives me minus z over 8. Then a half times z squared over 16. So I'll have z squared over 32. And then minus z cubed over 128. And this would carry on. So I have this expression, which is the partial fraction, corresponding to this one, subtracted by 1 over z plus 2. And we said that 1 over z plus 2 is this particular expansion. What we're going to do is merely take the expansion for 2 over z plus 4, and we're going to subtract it from the expansion of 1 over z plus 2. So our original function, which is z over z plus 2 times z plus 4, so that is equal to 2 over z plus 4 minus 1 over z plus 2. So this is the first series expansion, which is 1 over z minus 2 over z squared and so on. Oh, sorry, this was the first series expansion corresponding to this term. So that's a half minus z over 8, that's z over 8, plus z squared over 32 minus z cubed over 128. So we're now subtracting this, okay, and of course this carries on. So we're subtracting that from 1 over z, here's it here on the top, 1 over z minus 2 over z squared plus 4 over z cubed minus 8 over z to the power 4, and so on. So if we actually subtract this out and we carry on with this, then we can just write these terms first, and of course the sign of each one will change. We can just start off with the end. So we have plus, carrying on. So we have 8 over z to the power 4, and the sign will change because of the minus. So we have 8 over z to the power 4. Then we have minus 4 over z cubed. Then we have plus 2 over z squared. We have minus 1 over z. And then writing the rest of these terms, we have plus a half minus z over 8 plus z squared over 32 minus z cubed over 128. And this will continue. So this is kind of our Laurent series. Okay, so let's think about what we have. This term would correspond to z minus z naught to the minus 4 times a to the times a minus 4, and so on. And here we would have a minus 2 z minus z naught to the power minus 2. And then this term here would correspond to a naught. Then we would have a1 times z minus z naught to the power 1 plus a2 z minus z naught to the power 2. We can see that these terms correspond like that. Okay. So we integrate this. That's what we want to do. We want to integrate all of this. And we saw that in the Laurent series, when we integrate this function, okay, so what we're going to do now is we're going to integrate around this contour in this diagram we had drawn earlier of z over z plus 2, z plus 4. So when we do that, we had seen that all of these terms become 0, besides the one associated with the exponent to the minus 1. And we had seen that this gives us j times 2 pi times this residue a minus 1. And just looking at the series, okay, obviously z0 is 0 here. So this exponent where we have a minus 1, that's actually equal to minus 1. So there's it here. That's what our exponent is. That's what, sorry, not exponent, coefficient is. You can see it's minus 1. So this integral around this contour is equal to j 2 pi times minus 1. So we can just write a minus in front of it. So that's this integral evaluated. But we can see that this was not a very good methodology because it was quite a lengthy procedure to find this Laurent series. So in some instances, we can actually look at a shortcut to try and find the residues. So we have a shortcut. And this is applied to poles. So if the singular value is poles of order n, then we can apply the shortcut. So what we do is we take our function z, okay, then we multiply it by z minus z0 to the power n, okay, and then we take the derivative of n minus 1 of this product that we had just seen, and the denominator is dz to the n minus 1 since we're taking the derivative, and then we multiply it by 1 over n minus 1 factorial, and then we take the limit of this entire thing. We take the limit as z approaches z0. So what does this give you? It gives you the residue. That is what this expression gives you. So we can see this illustrated in a simple example. So let's just say we have fz is equal to z squared over z plus 2 squared. So this is a pole of order 2. Okay, we can see that the 2 there is in the exponent. So this is a pole of order 2. And we can apply this expression to find the residue. So a minus 1, the residue is firstly equal to, we take our function fz, so that's z squared over z plus 2 squared. Also, this pole is the singular value where z is equal to minus 2. So that's where the singular value is. So then we multiply it by this z minus z0 to the power n, and z0 is the singular value, that's minus 2. So instead of z0, we put in minus 2. So then we're multiplying it by z plus 2 raised to the power n, so squared. So essentially we are cancelling the denominator of this function. And we're taking the derivative of this, whole thing. dz, so n minus 1 is 1, so it's a first order derivative. And we're multiplying this by 1 over n minus 1 factorial, so n is 2. So we can just substitute that in, and we can just say 1 over 1 factorial. This entire thing, we're taking the limit as z approaches minus 2. So let's simplify this. That and that will cancel. Okay, so we have the limit as z approaches minus 2 of essentially d dz of z squared. That's what all of this comes down to. So that is the limit as z approaches minus 2 of 2z, which is just minus 4. So this is what the residue is. And you can see that this much simpler approach, the shortcut for this particular scenario where we have a pole of a certain order, gives us a very simple way of determining the residue of a function. So thank you very much for watching.